Picture this, a universe cloaked in darkness, silent and empty, with no stars, no galaxies, and no light. Now imagine the moment that darkness shattered, not with a bang, but with the faintest flicker of the very first star. This is the cosmic dawn era, a time when the universe woke up from its long, dark slumber and began to sparkle with the birth of the first stars and galaxies. But here's the thing, this era is filled with mysteries so profound, they challenge everything we think we know about the cosmos. How did the first stars ignite in a universe made only of hydrogen and helium? What triggered the end of the cosmic dark ages? And why do some of the earliest galaxies seem to defy the rules of time itself? Over the next few minutes, we're diving into 50 of the most mind-bending mysteries of the cosmic dawn era. From the elusive population 3 stars to the cosmic web that holds the universe together, each mystery will take us closer to understanding how our universe came to be. So, if you're ready to unravel the secrets of the cosmic dawn, let's get started, because the story of the universe's first light is waiting to be told. Now, let's turn our attention to the very first stars, the pioneers of light in a universe that had known only darkness. These stars, known as population 3 stars, are unlike anything we see today. Imagine a universe made entirely of hydrogen and helium, no heavy elements, no planets, no galaxies. In this pristine environment, the first stars had to form from scratch, relying solely on gravity to pull together clouds of gas. But here's the mystery. How did these stars ignite without the heavier elements that help cool gas and trigger star formation in the modern universe? One theory suggests that these stars were giants, hundreds or even thousands of times more massive than our Sun. Their immense size would have made them incredibly bright, but also short-lived, burning through their fuel in just a few million years. Yet, despite their brilliance, we've never directly observed a population 3 star. Why? Because they existed so long ago, their light has traveled billions of years to reach us, stretched and dimmed by the expansion of the universe. What's more, these stars likely exploded in spectacular supernova, scattering the first heavy elements into space and paving the way for future generations of stars and galaxies. So, while we can't see them directly, their fingerprints are everywhere. The elements they forged, carbon, oxygen, and iron, are the building blocks of everything around us, including you and me. The mystery of the first stars isn't just about how they formed, but how they shaped the universe we know today. And as we continue to search for clues in the faint echoes of their light, we're reminded that every star in the night sky owes its existence to these ancient pioneers. Next, we'll explore another cosmic puzzle, the epoch of reionization, a time when the universe underwent a dramatic transformation, transitioning from darkness to light. What caused this shift, and how did it shape the cosmos as we know it? Stay tuned. Now, let's journey into one of the most transformative periods in cosmic history, the epoch of reionization. Picture the universe as a vast, dark ocean filled with neutral hydrogen gas. For hundreds of millions of years after the Big Bang, this gas absorbed all light, leaving the cosmos in a state of near total darkness. But then, something extraordinary happened. The universe began to glow as if someone had flipped a cosmic switch. This was the epoch of reionization, a time when the first stars and galaxies lit up the cosmos, ionizing the surrounding gas and transforming the universe into the bright, transparent expanse we see today. But how did this dramatic shift occur? The answer lies in the first stars and galaxies. These early cosmic structures emitted intense ultraviolet light, which stripped electrons from hydrogen atoms, turning neutral gas into ionized plasma. Think of it like a giant cosmic flashlight piercing through the darkness and illuminating the universe. However, the details of this process remain shrouded in mystery. For instance, we don't fully understand how the first stars and galaxies produced enough energy to reionize the entire universe. Were there more of these early structures than we've detected? Or did they emit more ultraviolet light than we've estimated? Another puzzle is the timing of reionization. Observations suggest that this process didn't happen all at once but unfolded over hundreds of millions of years. Some regions of the universe became ionized earlier than others, creating a patchwork of light and darkness. Why did this happen? Was it due to variations in the density of gas, or did the first galaxies form in clusters, creating pockets of intense radiation? These questions challenge our understanding of the early universe and push astronomers to refine their models and observations. The epoch of reionization wasn't just a cosmic light show. It was a turning point that shaped the universe's future. By ionizing the gas, it allowed light to travel freely, paving the way for the formation of galaxies, stars, and planets. Yet, despite its importance, this era remains one of the least understood chapters in cosmic history. As we peer deeper into the universe's past, using tools like the James Webb Space Telescope, we hope to uncover more clues about this pivotal moment. Next, we'll delve into another enigma of the cosmic dawn era, the missing dark matter. Why does this mysterious substance, which makes up most of the universe's mass, seem to behave differently during this early period? Stay with us as we explore this cosmic conundrum. Now, let's turn our attention to one of the most puzzling aspects of the cosmic dawn era, the missing dark matter. Dark matter, that invisible and mysterious substance that makes up most of the universe's mass, played a critical role in shaping the cosmos. It acted like a cosmic scaffold, pulling gas together to form the first stars and galaxies. But here's the twist: during the cosmic dawn era, dark matter seems to have behaved in ways that don't quite match our expectations. Why is that, and what does it tell us about the early universe? To understand this mystery, let's first revisit what we know about dark matter. It doesn't interact with light, making it invisible to our telescopes. Yet, its gravitational influence is undeniable. In the modern universe, dark matter forms vast halos around galaxies, holding them together like an invisible glue. But during the cosmic dawn era, something unusual appears to have happened. Observations suggest that dark matter may have been less concentrated or distributed differently than it is today. This raises a big question. Did dark matter evolve over time, or were the conditions in the early universe so unique that it behaved in unexpected ways? One possibility is that the first stars and galaxies influenced dark matter in ways we're only beginning to understand. For example, the intense radiation from the first stars might have heated the surrounding gas, altering how dark matter clumped together. Another theory suggests that dark matter particles themselves might have interacted with each other or with ordinary matter in ways that are no longer common in the universe. These interactions could have slowed down the formation of dark matter halos, creating a more diffused distribution during the cosmic dawn era. But why does this matter? Well, understanding how dark matter behaved in the early universe could help us solve one of the biggest mysteries in cosmology: what dark matter actually is. By studying its role during the cosmic dawn era, we might uncover clues about its nature and how it shaped the universe's evolution. For instance, if dark matter particles are lighter or more interactive than we've assumed, it could explain why they behaved differently in the past. This mystery also highlights the challenges of studying the cosmic dawn era. Because dark matter doesn't emit light, we can't observe it directly. Instead, we have to infer its presence and behavior from its gravitational effects on visible matter. This makes it incredibly difficult to piece together a clear picture of what was happening billions of years ago. Yet, with advanced telescopes and simulations, scientists are slowly unraveling this cosmic puzzle. As we continue to explore the cosmic dawn era, the missing dark matter remains a tantalizing enigma. It challenges our understanding of the universe's most abundant yet elusive substance and pushes us to rethink our models of cosmic evolution. Next, we'll dive into another fascinating mystery of this era, the first black holes. How do these cosmic giants form so quickly after the Big Bang? Stay tuned as we uncover the secrets of the universe's earliest supermassive black holes. Now, let's shift our focus to another mind-bending mystery of the cosmic dawn era, the first black holes. These cosmic giants, some of the most powerful and enigmatic objects in the universe, seem to have appeared incredibly early in cosmic history. But how did supermassive black holes, with masses millions or even billions of times that of our Sun, form so quickly after the Big Bang? This question has puzzled scientists for decades, and the answers could reshape our understanding of the early universe. To tackle this mystery, let's start with what we know about black holes today. Typically, black holes form when massive stars collapse at the end of their lives, creating a region of space where gravity is so strong that not even light can escape. But the supermassive black holes we see in the centers of galaxies today are far too large to have formed this way. They would have needed billions of years to grow through the gradual accumulation of matter, yet we've observed them in galaxies that existed when the universe was less than 1 billion years old. So how did they get so big, so fast? One leading theory is called direct collapse. Imagine a massive cloud of gas in the early universe collapsing under its own gravity. Instead of fragmenting into smaller clumps that form stars, this cloud collapses directly into a black hole. This process could create a black hole with a mass tens of thousands of times that of the Sun in a single step. These seed black holes could then grow rapidly by devouring surrounding gas and merging with other black holes, eventually becoming the supermassive black holes we observe today. But direct collapse isn't the only possibility. Another theory suggests that the first black holes formed from the remnants of the very first stars, known as population 3 stars. These stars were incredibly massive and short-lived, ending their lives in spectacular supernovae that left behind black holes. Over time, these black holes could have merged and grown, feeding on the abundant gas in the early universe. However, this process would still require an extraordinary rate of growth to explain the supermassive black holes we see so early in cosmic history. The implications of these theories are profound. If direct collapse is the primary mechanism, it suggests that the early universe was filled with massive, dense clouds of gas that could bypass star formation entirely. This would mean that the first black holes played a crucial role in shaping the evolution of galaxies, influencing how stars and galaxies formed around them. On the other hand, if the first black holes grew from the remnants of population 3 stars, it would highlight the importance of these early stars in seeding the universe's structure. Understanding the origins of the first black holes isn't just about solving a cosmic puzzle, it's about uncovering the fundamental processes that shaped the universe as we know it. These black holes are thought to have played a key role in the formation of galaxies, the distribution of matter, and even the reionization of the universe. By studying them, we're not just looking back in time, we're piecing together the story of how everything came to be. As we continue to explore the cosmic dawn era, the mystery of the first black holes remains a cornerstone of our quest to understand the universe's origins. Next, we'll turn our attention to another intriguing puzzle, the strange patterns and anomalies in the cosmic microwave background. What do these ancient echoes of the Big Bang tell us about the early universe? Stay tuned as we unravel the secrets of the cosmic microwave background. Now, let's journey deeper into the mysteries of the cosmic dawn era by exploring one of the most fascinating relics of the early universe, the cosmic microwave background, or CMB. This faint glow, often called the afterglow of the Big Bang, is the oldest light we can observe, dating back to when the universe was just 380,000 years old. But within this ancient light, scientists have discovered strange patterns and anomalies that challenge our understanding of the universe's infancy. The cosmic microwave background is remarkably uniform, a testament to the universe's early state of near-perfect smoothness. However, when we look closely, subtle irregularities emerge, tiny fluctuations in temperature that reveal the seeds of cosmic structure. These fluctuations are like cosmic fingerprints, showing us where matter began to clump together, eventually forming galaxies and galaxy clusters. But some of these patterns don't quite fit our expectations, hinting at physics we don't yet fully understand. One of the most puzzling anomalies is the so-called cold spot, a region in the CMB that is significantly colder than its surroundings. This cold spot spans an area of the sky about 10 times the size of the full moon, and its existence is difficult to explain using our current models of the universe. Some theories suggest it could be evidence of a collision with another universe during the early moments of cosmic inflation, while others propose it might be caused by a vast cosmic void, a region of space with far fewer galaxies than expected. Either way, the cold spot challenges our understanding of the universe's large-scale structure. Another intriguing anomaly is the asymmetry in the CMB's temperature distribution. When we map the CMB, we find that one half of the sky is slightly warmer than the other. This dipole asymmetry shouldn't exist if the universe is isotropic, meaning it looks the same in all directions. Some scientists speculate that this asymmetry could be a sign of new physics at play during the cosmic dawn era, perhaps related to the mysterious forces that drove cosmic inflation. Then there's the mystery of the CMB's alignment with the solar system. Certain large-scale features in the CMB appear to align with the plane of our solar system, a phenomenon known as the axis of evil. This alignment is statistically unlikely and raises questions about whether our observations are being influenced by something we haven't accounted for, or if it's a clue to deeper cosmic truths. Could this alignment be a sign of new physics, or is it simply a coincidence? The answer remains elusive. These anomalies in the cosmic microwave background are more than just curiosities, they're windows into the unknown. They suggest that our current understanding of the universe's early moments is incomplete, and that there may be forces or phenomena at work during the cosmic dawn era that we have yet to discover. By studying these patterns, scientists hope to uncover new insights into the nature of dark energy, the behavior of gravity on cosmic scales, and even the possibility of other universes beyond our own. As we continue to probe the mysteries of the cosmic microwave background, we're reminded that the universe is full of surprises. These ancient echoes of the Big Bang hold secrets that could reshape our understanding of reality itself. Next, we'll turn our attention to another cornerstone of the cosmic dawn era, the formation of the first galaxies. How did these early structures come together, and why do some appear to defy our expectations? Stay tuned as we unravel the story of the universe's first galaxies. Now, let's shift our gaze to one of the most profound mysteries of the cosmic dawn era, the formation of the first galaxies. These ancient structures, born from the primordial soup of hydrogen and helium, mark the universe's transition from a dark, featureless expanse to a vibrant tapestry of light and structure. But how did these first galaxies come into being, and why do some of them seem to defy our expectations, appearing more massive and mature than they should for their age? The story of the first galaxies begins with the collapse of dark matter halos, vast clouds of invisible matter that served as the scaffolding for cosmic structure. Within these halos, gas began to cool and condense, eventually igniting the first stars. These stars, in turn, clustered together, forming the earliest protogalaxies. Over time, these protogalaxies merged and grew, evolving into the galaxies we recognize today. But this process, while seemingly straightforward, is riddled with questions. One of the most puzzling aspects of the first galaxies is their apparent maturity. Observations from powerful telescopes like the James Webb Space Telescope have revealed galaxies that existed just a few 100 million years after the Big Bang, yet they appear surprisingly well developed. Some of these galaxies are not only massive but also exhibit complex structures such as spiral arms and central bulges. features we typically associate with much older galaxies. How could such mature structures form so quickly in the universe's infancy? One theory suggests that the first galaxies may have formed in regions of the universe where matter was unusually dense, allowing them to grow and evolve at an accelerated rate. Another possibility is that the first stars and galaxies formed much earlier than we currently estimate, giving them more time to develop. Alternatively, these galaxies might have experienced rapid bursts of star formation, fueled by an abundance of gas and frequent collisions with other protogalaxies. Each of these scenarios challenges our understanding of galaxy formation and pushes us to rethink the timeline of cosmic evolution. Another mystery lies in the role of supermassive black holes in the early universe. Some of the first galaxies appear to host incredibly massive black holes at their centers, far larger than what we'd expect for such young systems. How did these black holes grow so quickly? Did they form directly from the collapse of massive gas clouds, or were they seeded by the remnants of the first stars? The answers to these questions could reshape our understanding of how galaxies and black holes co-evolve. The study of the first galaxies also raises questions about the nature of dark matter. While dark matter played a crucial role in providing the gravitational pull needed to form galaxies, its exact properties remain elusive. Could dark matter have behaved differently during the cosmic dawn era, influencing the formation and growth of galaxies in ways we don't yet understand? Or are we missing something fundamental about the interplay between dark matter and ordinary matter in the early universe? As we continue to explore these ancient galaxies, we're reminded that the universe is full of surprises. The first galaxies are not just relics of the past, they're keys to unlocking the secrets of cosmic evolution. By studying their formation and growth, we gain insights into the forces that shaped the universe and the processes that gave rise to the galaxies we see today. Next, we'll delve into another fascinating feature of the cosmic dawn era: the Lyman alpha forest, a cosmic phenomenon that offers a unique window into the distribution of gas in the early universe. Stay tuned as we uncover more mysteries of the cosmic dawn. Now, let's turn our attention to a fascinating cosmic phenomenon that acts like a fingerprint of the early universe: the Lyman alpha forest. This intricate web of absorption lines, observed in the light of distant quasars, offers a unique glimpse into the distribution of gas during the cosmic dawn era. But what exactly is the Lyman alpha forest, and why is it such a powerful tool for understanding the universe's infancy? The Lyman alpha forest gets its name from the way it appears in the spectra of quasars, the incredibly bright cores of distant galaxies powered by supermassive black holes. As light from these quasars travels through the cosmos, it passes through clouds of hydrogen gas. When this light reaches us, it carries with it a record of its journey, a series of dark absorption lines known as the Lyman alpha forest. Each line corresponds to a specific wavelength of light absorbed by hydrogen atoms, revealing the presence of gas clouds at different distances along the line of sight. But why is this important? The Lyman alpha forest acts like a cosmic map, showing us where gas was distributed in the early universe. During the cosmic dawn era, the universe was filled with a diffuse fog of neutral hydrogen. As the first stars and galaxies formed, their intense radiation began to ionize this gas, carving out bubbles of ionized hydrogen. The Lyman alpha forest captures this transition, allowing us to study how the universe evolved from a neutral state to one filled with ionized gas. One of the most intriguing aspects of the Lyman alpha forest is its ability to reveal the large-scale structure of the early universe. The distribution of gas clouds isn't random. It follows the underlying cosmic web, the vast network of filaments and voids that make up the universe's skeleton. By analyzing the patterns in the Lyman alpha forest, astronomers can trace the growth of this cosmic web and understand how matter clumped together to form the first galaxies and galaxy clusters. However, the Lyman alpha forest also presents its own set of mysteries. For instance, the exact nature of the gas clouds and their relationship to the first galaxies remains unclear. Are these clouds remnants of the early universe, or are they part of the intergalactic medium that was later enriched by the first stars? Additionally, the precise mechanisms that caused the gas to ionize and form the forest are still being debated. Did the first stars and galaxies alone drive this process, or did other factors like quasars or even dark matter play a role? The study of the Lyman alpha forest is a testament to the ingenuity of astronomers. By decoding the subtle patterns in quasar light, they've unlocked a treasure trove of information about the early universe. This phenomenon not only helps us understand the distribution of gas during the cosmic dawn era, but also sheds light on the forces that shaped the cosmos into what we see today. Next, we'll explore another enigma of this era, the mystery of the missing baryons, and why a significant portion of the universe's normal matter seems to have vanished during this critical period. Stay with us as we continue unraveling the secrets of the cosmic dawn. Now, let's shift our focus to one of the most puzzling questions in cosmology, the mystery of the missing baryons. Baryons, the building blocks of normal matter, make up everything we can see: stars, planets, galaxies, and even ourselves. Yet during the cosmic dawn era, a significant portion of these baryons seems to have vanished without a trace. Where did they go, and why can't we find them? To understand this mystery, we first need to grasp what baryons are and why they're so important. Baryons include protons and neutrons, the particles that form the nuclei of atoms. They're a fundamental part of the universe's visible structure, and according to our best estimates, they should account for about 5% of the universe's total mass and energy. But here's the catch. When astronomers tally up all the baryons they can observe in stars, galaxies, and gas clouds, they find that a large fraction is missing. This discrepancy is especially pronounced during the cosmic dawn era, a time when the first structures were forming. So where could these missing baryons be hiding? One leading theory suggests they're spread out in the form of hot, diffuse gas in the intergalactic medium, the vast spaces between galaxies. This gas is incredibly difficult to detect because it's so thin and doesn't emit much light. However, it's not completely invisible. By studying the way light from distant quasars and galaxies passes through this gas, astronomers have found hints of its presence. These observations reveal a faint, wispy network of gas filaments, often referred to as the cosmic web, which may contain the missing baryons. Another possibility is that the missing baryons are hiding in the form of warm, hot intergalactic medium, or WIM. This gas is slightly denser and hotter than the diffuse intergalactic medium, making it even harder to detect. It's thought to reside in the outskirts of galaxy clusters and along the filaments of the cosmic web. While we've caught glimpses of the WIM through X-ray and ultraviolet observations, it's still a challenge to map its full extent and confirm whether it holds the key to the missing baryon problem. But why does this matter? Understanding where the missing baryons are isn't just an academic exercise, it's crucial for piecing together the history of the universe. Baryons played a vital role in the formation of the first stars and galaxies, and their distribution tells us how matter clumped together in the early universe. If a significant portion of baryons is unaccounted for, it could mean our models of cosmic evolution are incomplete or missing a critical piece of the puzzle. The search for the missing baryons is ongoing, with astronomers using a variety of techniques to track them down. From advanced telescopes that can detect faint X-ray emissions to simulations that model the behavior of gas in the early universe, scientists are leaving no stone unturned. Each new discovery brings us closer to solving this cosmic mystery and understanding how the universe took shape during its formative years. As we continue our journey through the mysteries of the cosmic dawn era, we'll next explore another fascinating enigma: the role of magnetic fields in the early universe. How did these invisible forces originate, and what impact did they have on the formation of the first stars and galaxies? Stay tuned as we dive deeper into the forces that shape the cosmos. Now, let's turn our attention to another captivating mystery of the cosmic dawn era, the role of magnetic fields. These invisible forces are everywhere in the universe today, shaping everything from the motion of charged particles to the structure of galaxies. But how did they first emerge, and what part did they play in the formation of the earliest stars and galaxies? This is a question that has puzzled scientists for decades, and the answers could reshape our understanding of the universe's infancy. Magnetic fields are essentially regions of space where charged particles, like electrons and protons, experience a force. They're generated by the movement of these charged particles, often in the form of electric currents. Today, we see magnetic fields in stars, planets, and even entire galaxies. But in the early universe, before stars and galaxies existed, the conditions were very different. The universe was filled with a hot, dense plasma of charged particles, but it's unclear how magnetic fields could have formed in such a chaotic environment. One leading theory suggests that magnetic fields were born during the period of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. Tiny quantum fluctuations during this time could have created weak magnetic fields on incredibly small scales. As the universe expanded, these fields might have stretched and grown, eventually becoming the large-scale magnetic fields we observe today. Another possibility is that magnetic fields were generated by the first stars and galaxies themselves. As these structures formed, the movement of charged particles within them could have amplified weak magnetic fields, turning them into the powerful forces we see now. But why does this matter? Magnetic fields play a crucial role in shaping the universe. They influence how gas collapses to form stars, how galaxies evolve, and even how cosmic rays travel through space. Without magnetic fields, the universe as we know it might look very different. For example, magnetic fields can prevent gas from collapsing too quickly, allowing stars to form more slowly and efficiently. They also help regulate the flow of energy within galaxies, influencing how stars and black holes grow. During the cosmic dawn era, magnetic fields might have had an even more profound impact. As the first stars and galaxies began to form, these fields could have guided the flow of gas, helping it clump together into denser regions. This process would have been essential for the formation of the first structures, as it allowed matter to accumulate and eventually ignite the first stars. Magnetic fields might also have played a role in the distribution of heavy elements, which were forged in the hearts of these early stars and spread throughout the universe by supernova explosions. Despite their importance, magnetic fields from the cosmic dawn era are incredibly difficult to study. They don't emit light, and their effects are often subtle and indirect. However, astronomers have developed clever ways to detect them. For instance, by studying the polarization of light from distant galaxies and quasars, scientists can infer the presence of magnetic fields along the line of sight. Simulations of the early universe also provide valuable insights, helping researchers understand how magnetic fields might have evolved over time. The mystery of magnetic fields in the early universe is far from solved, but each new discovery brings us closer to understanding their origins and impact. As we continue to explore the cosmic dawn era, we'll next delve into another fascinating enigma, the formation of the first molecules. How did simple atoms come together to create the building blocks of stars and planets? Stay with us as we uncover the secrets of the universe's first chemistry. Now, let's shift our focus to a cornerstone of the cosmic dawn era, the formation of the first molecules. These simple yet crucial compounds, like molecular hydrogen, played a pivotal role in shaping the early universe. Without them, the gas that filled the cosmos might never have cooled enough to collapse into the first stars and galaxies. So, how did these molecules come to be, and why were they so essential? In the early universe, the only elements present were hydrogen and helium created during the Big Bang. For stars and galaxies to form, this gas needed to cool and clump together. But cooling requires energy to be released, and that's where molecules come in. Molecular hydrogen, made up of two hydrogen atoms, was one of the first molecules to form. It acted like a cosmic refrigerator, allowing gas to shed heat and condense into denser regions. The process of forming molecular hydrogen wasn't straightforward. In the beginning, the universe was too hot and energetic for atoms to bond. Electrons and protons were zipping around too fast to stick together. But as the universe expanded and cooled, electrons began to pair with protons, forming neutral hydrogen atoms. This period, known as recombination, set the stage for the next critical step, the formation of molecules. Molecular hydrogen likely formed on the surfaces of tiny dust grains or through reactions involving free electrons. These grains acted as catalysts, providing a surface where hydrogen atoms could meet and bond. Once formed, molecular hydrogen played a key role in cooling the gas. When hydrogen molecules collide, they can release energy in the form of light, allowing the gas to lose heat and become denser. This cooling effect was essential for the gas to collapse under its own gravity, eventually igniting the first stars. But molecular hydrogen wasn't the only player. Other simple molecules like helium hydride also formed during this time. Helium hydride, made of helium and hydrogen, is thought to be the very first molecule in the universe. While it didn't play as significant a role in cooling as molecular hydrogen, its existence marks a crucial milestone in the universe's chemical evolution. The formation of these molecules wasn't just a matter of chemistry, it was a cosmic turning point. Without them, the gas in the early universe would have remained too hot and diffused to form stars. The first molecules acted as the universe's first building blocks, setting the stage for the birth of stars, galaxies, and eventually planets like our own. Studying these early molecules is no easy task. They existed billions of years ago, and their traces are faint. However, astronomers have found ways to detect them indirectly. By observing distant clouds of gas and analyzing the light they emit, scientists can infer the presence of molecular hydrogen and other early molecules. Simulations of the early universe also help researchers understand how these molecules formed and influenced the cosmos. The story of the first molecules is a testament to the delicate balance of forces that shaped our universe. As we continue to explore the cosmic dawn era, we'll next uncover another mystery: what exactly triggered the end of the cosmic dark ages and ushered in the era of light. Stay tuned as we unravel the secrets of the universe's first dawn. Now, let's step into one of the most pivotal moments in cosmic history, the end of the cosmic dark ages. This mysterious transition marked the universe's shift from a vast, dark expanse to a glowing, star-filled cosmos. But what exactly caused this dramatic change? What forces or events lit the fuse that brought light to the universe? The cosmic dark ages began after the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. During this time, the cosmos was shrouded in darkness. There were no stars, no galaxies, and no sources of light. The universe was a cold, quiet place filled with gas and the faint afterglow of the Big Bang. But this darkness didn't last forever. Something had to break the silence and ignite the first sparks of light. The key to ending the dark ages lies in the formation of the first stars and galaxies. These cosmic pioneers were the universe's first light sources, and their birth marked the beginning of the cosmic dawn. But how did this happen? The process began with the collapse of dense regions of gas, which had been cooling and clumping together thanks to molecules like molecular hydrogen. As these gas clouds grew denser, gravity took over, pulling the gas into tighter and tighter knots. Eventually, the pressure and temperature at the cores of these knots became so intense that nuclear fusion ignited and the first stars were born. These first stars, known as population 3 stars, were unlike anything we see today. They were massive, hot, and incredibly bright, flooding the universe with ultraviolet light. This light didn't just illuminate the cosmos, it also began to ionize the surrounding hydrogen gas. As the star's radiation spread, it stripped electrons from hydrogen atoms, turning the neutral gas into a sea of charged particles. This process, known as reionization, marked the end of the Dark Ages and the beginning of a new era filled with light and structure. But the story doesn't end there. The first stars didn't just light up the universe, they also seeded it with the first heavy elements. When these massive stars died in spectacular supernova explosions, they scattered elements like carbon, oxygen, and iron into the surrounding gas. These elements would later become the building blocks for future stars, planets, and even life itself. The end of the Dark Ages wasn't just a single event, it was a gradual process that unfolded over hundreds of millions of years. It involved the birth and death of countless stars, the formation of the first galaxies, and the transformation of the universe's gas from neutral to ionized. Yet, despite our growing understanding, many questions remain. For instance, what role did the first black holes play in this process? Did they contribute to reionization, or did they form later? And how did the first galaxies influence the spread of light across the cosmos? As we continue to explore this cosmic turning point, we're reminded of how interconnected the universe's history is. The end of the Dark Ages set the stage for everything that followed, from the formation of galaxies to the emergence of life. And as we peer deeper into the cosmos, we're uncovering clues that bring us closer to understanding this profound transition. Next, we'll explore another fascinating mystery: the impact of the first supernova on the early universe. How did these explosive events shape the cosmos, and what legacy did they leave behind? Stay with us as we journey deeper into the cosmic dawn era. Now, let's turn our attention to one of the most explosive events in the early universe, the first supernova. These cataclysmic explosions didn't just mark the dramatic deaths of the first stars, they also played a crucial role in shaping the cosmos as we know it today. When the earliest stars, those massive population 3 stars, reached the end of their lives, they didn't fade quietly. Instead, they went out with a bang, literally. These supernovae were so powerful that they sent shockwaves rippling through the universe, scattering the heavy elements forged in their cores far and wide. The first supernovae were cosmic alchemists, transforming the simple elements of hydrogen and helium into heavier ones like carbon, oxygen, and iron. These elements, created in the intense heat and pressure of stellar cores, were blasted into space during the explosions. This process, known as nucleosynthesis, seeded the universe with the building blocks for everything that would come later: planets, moons, and even life itself. Without these early supernovae, the universe would have remained a barren place, filled only with the lightest elements. But the impact of these supernovae went beyond just enriching the cosmos with heavy elements. The shockwaves from these explosions also played a key role in triggering the formation of new stars and galaxies. As the shockwaves traveled through space, they compressed nearby gas clouds, causing them to collapse under their own gravity. This compression ignited the birth of the next generation of stars, setting off a chain reaction of star formation that would continue for billions of years. In this way, the first supernova didn't just end the lives of stars, they also helped create new ones. Interestingly, the first supernova may have also influenced the structure of the early universe. The energy released by these explosions could have heated the surrounding gas, preventing it from collapsing too quickly and regulating the pace of star formation. This feedback mechanism ensured that stars didn't form all at once, but rather in a more controlled and gradual process. It's a delicate balance that helped shape the distribution of galaxies we see today. Yet, despite their importance, many questions about the first supernova remain. For instance, how massive were these early stars, and how did their explosions differ from the supernova we observe today? Did they leave behind black holes or neutron stars? And if so, how did these remnants influence their surroundings? And what role did these supernovae play in the larger story of cosmic evolution, from the formation of galaxies to the emergence of life? As we piece together the clues left behind by these ancient explosions, we gain a deeper appreciation for their role in the universe's history. The first supernovae were not just destructive events, they were also creative forces, shaping the cosmos in ways that continue to echo through time. Their legacy is written in the stars, the planets, and even in us. Next, we'll explore another intriguing mystery, the formation of quasars, the brightest objects in the universe. How did these luminous powerhouses form so early, and what do they tell us about the conditions of the cosmic dawn era? Stay with us as we continue our journey through the mysteries of the early universe. Now, let's shift our gaze to one of the most dazzling enigmas of the early universe, quasars. These luminous powerhouses, often referred to as the brightest objects in the cosmos, have puzzled astronomers for decades. How did they form so soon after the Big Bang, and what secrets do they hold about the cosmic dawn era? Quasars are essentially supermassive black holes at the centers of young galaxies, gobbling up vast amounts of gas and dust. As this material spirals into the black hole, it heats up to incredible temperatures, releasing enormous amounts of energy in the form of light. This makes quasars visible across billions of light years, shining brighter than entire galaxies. But here's the mystery. How did these supermassive black holes grow so massive so quickly in the early universe? One leading theory suggests that quasars formed from the direct collapse of massive gas clouds. In the dense, chaotic environment of the cosmic dawn era, these clouds could have collapsed under their own gravity, bypassing the usual process of star formation and instead creating black holes with masses millions or even billions of times that of our Sun. Another possibility is that smaller black holes merged over time, growing into the behemoths we see as quasars. What makes quasars particularly fascinating is the light they emit. This light carries clues about the conditions of the early universe, such as the density and temperature of the gas surrounding them. By studying quasars, astronomers can peer back in time to an era when the universe was still in its infancy, filled with swirling gas and the first flickers of starlight. But quasars aren't just cosmic flashlights, they also played a role in shaping the universe. The intense radiation they emitted could have ionized nearby gas, contributing to the epoch of reionization, the period when the universe transitioned from being dark and neutral to filled with ionized gas. This process was crucial for allowing light to travel freely through space, setting the stage for the universe we see today. Yet many questions remain. Why do some quasars appear to be more active than others? What triggered their formation, and how did they influence the growth of their host galaxies? And perhaps most intriguingly, could quasars have played a role in seeding the universe with the heavy elements necessary for life? As we continue to unravel the mysteries of quasars, we gain not only a deeper understanding of these cosmic giants, but also a clearer picture of the universe's formative years. Their brilliance illuminates the past, offering us a glimpse into a time when the cosmos was young, chaotic, and full of potential. Next, we'll explore another captivating mystery, the formation of the first star clusters. How did these ancient gatherings of stars come together, and why do some appear to defy our understanding of cosmic timelines? Stay with us as we journey further into the mysteries of the cosmic dawn era. Now, let's turn our attention to another fascinating puzzle from the cosmic dawn era, the formation of the first star clusters. These ancient gatherings of stars born in the early universe hold secrets that challenge our understanding of cosmic timelines. How did these clusters come together, and why do some of them seem to defy the very age of the universe itself? Star clusters are groups of stars bound together by gravity, and they come in two main types: open clusters, which are relatively young and loosely bound, and globular clusters, which are older, denser, and often contain hundreds of thousands of stars. The first star clusters to form in the universe were likely globular clusters, emerging during a time when the cosmos was still in its infancy. But here's the twist: some of these ancient clusters appear to be older than the universe itself, or at least older than our current estimates of its age. So how did these clusters form in the first place? In the early universe, vast clouds of gas began to collapse under their own gravity, fragmenting into smaller clumps. These clumps eventually ignited, giving birth to the first stars. Over time, gravity pulled these stars together, forming the earliest star clusters. But the process wasn't straightforward. The intense radiation from the first stars and the chaotic environment of the cosmic dawn era made it difficult for stars to form and survive. Yet somehow, these clusters managed to emerge, becoming some of the oldest structures in the universe. The mystery deepens when we consider the age of these clusters. Some globular clusters, like those in our own Milky Way, are estimated to be around 13 billion years old, close to the age of the universe itself. But a few appear to be even older, raising questions about our understanding of cosmic timelines. Could our measurements be off, or is there something we're missing about how these clusters formed? One possibility is that the first star clusters formed in regions of the universe where conditions were just right, dense enough to allow stars to form quickly, but shielded from the intense radiation that might have disrupted their growth. Another theory suggests that these clusters might have formed from the remnants of even earlier stars, whose lifespans were incredibly short due to their massive size. These stars could have exploded as supernova, seeding the surrounding gas with heavy elements and triggering the formation of new stars in dense clusters. What's truly remarkable is that these ancient star clusters have survived for billions of years, enduring the turbulent evolution of the universe. They serve as cosmic time capsules, preserving clues about the conditions of the early universe. By studying them, astronomers can piece together the story of how the first stars and galaxies came to be, yet the mystery of their apparent age remains. Are we underestimating the age of the universe, or are these clusters simply the result of processes we don't yet fully understand? As we continue to explore the cosmic dawn era, these ancient star clusters remind us that the universe is full of surprises waiting to be uncovered. Next, we'll delve into the cosmic web, the intricate network of gas and dark matter that connects galaxies across the universe. How did this vast structure begin to take shape during the cosmic dawn era? Join us as we unravel this next mystery. Now, let's shift our gaze to one of the most awe-inspiring structures in the cosmos, the cosmic web. Imagine the universe as a vast, intricate tapestry, woven together by threads of gas and dark matter, connecting galaxies across unimaginable distances. This cosmic web is the backbone of the universe, and its origins trace back to the cosmic dawn era when the first seeds of structure began to grow. The cosmic web didn't form overnight. It began as tiny fluctuations in the density of matter, mere ripples in the fabric of the early universe. These ripples, born from the afterglow of the Big Bang, were the starting point for everything we see today. Over time, gravity took hold, pulling matter together into denser regions while leaving voids in between. This process created a network of filaments, long, thread-like structures of gas and dark matter that stretch across the universe, connecting galaxies and galaxy clusters like beads on a string. During the cosmic dawn era, the cosmic web began to take shape as the first stars and galaxies formed within these filaments. The densest regions of the web became the birthplaces of galaxies, while the voids remained largely empty. But the web wasn't static. It evolved as the universe expanded, growing more complex and interconnected. The first galaxies formed along these filaments, drawn together by gravity, and over billions of years, the cosmic web became the scaffolding for the large-scale structure of the universe we observe today. What's truly fascinating is how the cosmic web reflects the distribution of dark matter. Although invisible, dark matter makes up the majority of the universe's mass, and its gravitational pull shaped the web's formation. Ordinary matter, the gas that forms stars and galaxies, followed the dark matter's lead, flowing into the densest regions of the web. This interplay between dark and ordinary matter created the intricate patterns we see in the universe today, from the smallest galaxies to the largest superclusters. But the cosmic web isn't just a relic of the past, it's still evolving. Galaxies continue to move along the filaments, drawn toward the densest nodes where clusters of galaxies reside. These nodes are like cosmic cities, bustling with activity, while the filaments act as highways, guiding the flow of matter across the universe. Even now, the cosmic web is shaping the fate of galaxies, influencing where they form and how they grow. Studying the cosmic web gives us a glimpse into the universe's history and its future. By mapping its structure, astronomers can trace the growth of the universe from its earliest moments to the present day. It's a reminder that the universe is not a random collection of stars and galaxies, but a carefully woven tapestry, shaped by the forces of gravity and the mysteries of dark matter. As we continue to explore the cosmic dawn era, the cosmic web stands as a testament to the universe's complexity and beauty. It's a structure that connects everything from the smallest star to the largest galaxy cluster, and it holds the key to understanding how the universe came to be. Next, we'll uncover the mystery of the first heavy elements, how they were forged in the hearts of the earliest stars and scattered across the cosmos, paving the way for everything that followed. Stay with us as we dive into this next chapter of the cosmic dawn era. Now, let's turn our attention to one of the most transformative events in the history of the cosmos, the creation of the first heavy elements. Picture the early universe, a place filled with only the simplest ingredients: hydrogen, helium, and a trace of lithium. These were the building blocks of everything, but they were far from enough to create the rich diversity of matter we see today. So, how did the universe go from this sparse chemical palette to one brimming with elements like carbon, oxygen, and iron? The answer lies in the hearts of the first stars. When the first stars ignited, they didn't just light up the universe, they also became cosmic forges. These stars, known as population 3 stars, were massive and short-lived, burning through their fuel at an astonishing rate. Deep within their cores, temperatures and pressures reached unimaginable levels, allowing nuclear fusion to produce heavier elements. This process, known as stellar nucleosynthesis, transformed hydrogen and helium into carbon, oxygen, and even heavier elements like silicon and iron. But here's the catch: these heavy elements were trapped inside the stars. To spread them across the universe, something dramatic had to happen. That something was the death of these stars. When the first massive stars reached the end of their lives, they exploded in spectacular supernova, scattering their newly forged elements into the surrounding space. These explosions were so powerful that they not only enriched the cosmos with heavy elements, but also triggered the formation of new stars and galaxies. The distribution of these elements wasn't uniform, though. Some regions of the early universe became richer in heavy elements than others, creating pockets of chemical diversity. Over time, these elements mixed with the surrounding gas, forming the raw materials for future generations of stars, planets, and even life itself. Without these first heavy elements, the universe as we know it, with its planets, oceans, and living organisms, would never have come to be. Yet, the mystery doesn't end there. Scientists are still trying to understand exactly how these heavy elements spread so quickly across the early universe. Some theories suggest that the first stars weren't the only contributors. Black holes, neutron stars, and even cosmic collisions may have played a role in dispersing these elements. Each of these processes left its mark on the chemical makeup of the cosmos, creating a complex tapestry of elements that continues to evolve to this day. What's truly remarkable is how these heavy elements connect us to the earliest moments of the universe. Every atom of carbon in your body, every molecule of oxygen you breathe, was forged in the heart of a star billions of years ago. We are quite literally made of stardust, and the story of these first heavy elements is the story of our cosmic origins. As we continue to explore the cosmic dawn era, the mystery of the first heavy elements reminds us of the universe's incredible capacity for transformation. From the simplest beginnings, it has grown into a place of astonishing complexity, filled with the building blocks of life. Next, we'll delve into the role of dark energy and whether this mysterious force influenced the formation of structures during the cosmic dawn era. Stay with us as we uncover yet another layer of the universe's grand story. Now, let's shift our gaze to one of the most enigmatic forces in the cosmos, dark energy. This mysterious energy, which makes up about 68% of the universe, is responsible for the accelerating expansion of space itself. But here's the question: did dark energy play a role in shaping the structures we see during the cosmic dawn era? To understand this, we need to rewind to the early universe. During the cosmic dawn, the universe was much smaller and denser, with gravity acting as the dominant force. It was gravity that pulled matter together, forming the first stars, galaxies, and cosmic structures. But as the universe expanded, dark energy began to take over, pushing galaxies apart and accelerating the expansion of space. The tricky part is figuring out when dark energy started to influence the universe. During the cosmic dawn era, the universe was still relatively young, and dark energy's effects were much weaker compared to gravity. However, some scientists believe that even in these early stages, dark energy might have subtly influenced the way structures formed. For example, it could have affected the rate at which galaxies clustered together or the distribution of matter on the largest scales. One intriguing idea is that dark energy might have created a kind of cosmic tension, pulling space apart while gravity tried to pull matter together. This delicate balance could have shaped the way galaxies and clusters formed, leaving behind a unique fingerprint in the large-scale structure of the universe. But here's the challenge: detecting dark energy's influence during the cosmic dawn era is incredibly difficult. The effects are subtle, and the data we have from that time is limited. Astronomers rely on observations of the cosmic microwave background, the distribution of galaxies, and the way light bends around massive objects to piece together clues about dark energy's role. What makes this mystery even more fascinating is that dark energy's influence isn't constant. Over time, its effects have grown stronger as the universe has expanded. This means that while dark energy might not have been a major player during the cosmic dawn, it has become one of the most powerful forces shaping the universe today. As we continue to explore the cosmic dawn era, the question of dark energy's role remains open. Did it subtly guide the formation of the first structures, or was its influence too weak to make a difference? The answer could reshape our understanding of how the universe evolved from its earliest moments to the vast, complex cosmos we see today. Next, we'll venture into the possibility of planetary systems forming around the first stars. Could planets have existed in the earliest days of the universe? Stay with us as we uncover this intriguing chapter of cosmic history. Now, let's turn our attention to a fascinating question. Could planets have formed around the very first stars in the universe? Imagine a time when the cosmos was still in its infancy, filled with the glow of the first stars, and ask yourself, could these ancient stars have hosted their own planetary systems? To explore this, we need to consider the conditions of the cosmic dawn era. The first stars, known as population 3 stars, were massive, hot, and short-lived. They burned through their fuel quickly, ending their lives in spectacular supernova. But before they exploded, could they have had planets orbiting them? The answer lies in the ingredients needed to form planets. Planets are born from the leftover material in a star's protoplanetary disk, a swirling cloud of gas and dust that surrounds a young star. For planets to form, this disk needs to contain heavier elements like carbon, oxygen, and silicon, which are essential for building rocky planets and the cores of gas giants. Here's the catch: the first stars were made almost entirely of hydrogen and helium, the simplest elements in the universe. Heavier elements, which astronomers call metals, didn't exist yet. These metals were forged in the hearts of stars and scattered into space by supernova. So, in the earliest days of the universe, there simply wasn't enough material to form planets. But what about after the first stars exploded? Their deaths would have seeded the cosmos with the first heavy elements, enriching the surrounding gas clouds. This means that the second generation of stars, known as population 2 stars, might have had a better chance of hosting planets. These stars formed from gas that had been polluted by the remains of the first stars, giving them the raw materials needed to create planets. Even so, forming planets around these early stars would have been no easy feat. The universe was still a chaotic place with frequent supernova and intense radiation that could disrupt the delicate process of planet formation. Additionally, the first stars were so massive and energetic that their intense ultraviolet light might have blown away the gas and dust needed to form planets. Despite these challenges, some scientists believe that planets could have formed around the second generation of stars. These early planetary systems would have been very different from what we see today. For example, they might have been dominated by gas giants, as rocky planets require even more heavy elements to form. The search for these ancient planetary systems is ongoing. Astronomers are studying the oldest stars in our galaxy, looking for signs of planets that formed billions of years ago. If they find them, it could give us a glimpse into the very first planetary systems in the universe. So, while the first stars might not have had planets, their legacy paved the way for the cosmic diversity we see today. The heavy elements they created became the building blocks for everything that followed: stars, planets, and even life itself. Next, we'll dive into the mystery of gamma-ray bursts, the most energetic explosions in the universe, and their potential impact on the early cosmos. What role did these cosmic fireworks play during the cosmic dawn era? Stay tuned as we explore this explosive chapter of cosmic history. Now, let's shift our focus to one of the most dramatic events in the cosmos: gamma-ray bursts. These are the most powerful explosions in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. But what role did these colossal bursts of energy play during the cosmic dawn era, and how did they shape the early universe? Gamma-ray bursts are thought to occur when massive stars collapse into black holes or when neutron stars collide. These events unleash jets of energy that travel at nearly the speed of light, producing intense flashes of gamma rays. During the cosmic dawn era, when the first stars and galaxies were forming, gamma-ray bursts would have been far more common than they are today. This is because the universe was filled with massive, short-lived stars that were prone to such cataclysmic endings. But what impact did these bursts have on the early universe? For one, they could have played a significant role in reionizing the cosmos. The intense radiation from gamma-ray bursts would have ionized the surrounding gas, stripping electrons from atoms and contributing to the transition from a dark, neutral universe to one filled with light. This process was crucial for the formation of galaxies, as ionized gas is more likely to collapse and form stars. However, gamma-ray bursts weren't just creators, they were also destroyers. The same radiation that ionized gas could also strip away the atmospheres of nearby planets, making it difficult for life to emerge. In fact, some scientists believe that gamma-ray bursts might have sterilized entire regions of the early universe, preventing the formation of life until the rate of these explosions decreased. Another intriguing possibility is that gamma-ray bursts influenced the formation of early galaxies. The energy from these explosions could have triggered star formation in nearby gas clouds, acting as cosmic catalysts for the birth of new stars and galaxies. At the same time, the shock waves from gamma-ray bursts might have disrupted the delicate process of galaxy formation, creating chaotic environments where stars and galaxies struggle to take shape. Today, astronomers study gamma-ray bursts to learn more about the conditions of the early universe. By observing these distant explosions, they can piece together how the first stars and galaxies formed and evolved. Some gamma-ray bursts are so far away that their light has been traveling for billions of years, giving us a glimpse into the cosmic dawn era itself. As we continue to unravel the mysteries of gamma-ray bursts, one thing is clear: these cosmic fireworks were a defining feature of the early universe. They shaped the cosmos in ways we are only beginning to understand, leaving behind a legacy that continues to influence the universe today. Next, we'll explore the formation of the first neutron stars and their potential role in enriching the early universe with heavy elements. How did these incredibly dense objects contribute to the cosmic story? Stay tuned as we uncover the secrets of the first neutron stars. Now, let's turn our attention to another fascinating chapter in the story of the cosmic dawn era, the first neutron stars. These incredibly dense remnants of massive stars are among the most extreme objects in the universe, packing the mass of our Sun into a sphere no larger than a city. But how did these cosmic powerhouses form, and what role did they play in shaping the early universe? Neutron stars are born from the explosive deaths of massive stars in events known as supernova. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a cataclysmic explosion. What remains is a neutron star, a spinning, ultra-dense core composed almost entirely of neutrons. During the cosmic dawn era, when the first stars were massive and short-lived, neutron stars would have been among the earliest compact objects to form in the universe. But neutron stars aren't just relics of stellar death, they're also cosmic factories. One of their most significant contributions to the early universe was the production of heavy elements. When neutron stars collide, they release enormous amounts of energy and eject material rich in elements like gold, platinum, and uranium. These collisions, known as kilonovae, are thought to be one of the primary sources of heavy elements in the universe. Without neutron stars, the cosmos might have remained a much simpler place, devoid of the complex chemistry that makes planets and life possible. In addition to producing heavy elements, neutron stars also played a role in shaping their surroundings. Their intense magnetic fields and rapid rotation generate powerful beams of radiation, which can sweep across the cosmos like cosmic lighthouses. These beams, known as pulsars, can ionize nearby gas and influence the formation of stars and galaxies. Some scientists even speculate that the radiation from neutron stars could have contributed to the reionization of the universe, helping to end the cosmic dark ages. But neutron stars are more than just cosmic tools, they're also windows into the physics of extreme environments. The conditions inside a neutron star are so extreme that they challenge our understanding of matter itself. At their cores, the pressure is so intense that protons and electrons merge to form neutrons, creating a state of matter that doesn't exist anywhere else in the universe. Studying neutron stars gives us insights into the fundamental forces that govern the cosmos, from gravity to nuclear physics. As we continue to explore the mysteries of the cosmic dawn era, neutron stars stand out as key players in the story of the early universe. They enriched the cosmos with heavy elements, influenced the formation of galaxies, and pushed the boundaries of our understanding of physics. Their legacy is written in the stars and planets around us, a testament to the dynamic and interconnected nature of the universe. Next, we'll dive into the mystery of cosmic inflation and how this rapid expansion of the early universe might have set the stage for the formation of the first structures. What clues does this era hold about the origins of everything we see today? Stay tuned as we unravel the secrets of cosmic inflation. Now, let's step back in time to an even earlier chapter in the universe's history, cosmic inflation. This mysterious period, which unfolded in the tiniest fraction of a second after the Big Bang, is thought to have set the stage for everything that followed, including the formation of the first stars and galaxies during the cosmic dawn era. But what exactly was cosmic inflation, and how did it shape the universe we see today? Cosmic inflation refers to a brief but incredibly rapid expansion of space itself, during which the universe grew exponentially in size. Imagine blowing up a balloon to an enormous scale in the blink of an eye. That's the kind of expansion we're talking about. This explosive growth didn't just make the universe bigger, it also smoothed out its irregularities, creating a remarkably uniform cosmos. However, it wasn't perfectly smooth. Tiny quantum fluctuations, like ripples on the surface of a pond, were stretched across the universe during inflation, leaving behind faint imprints that would later become the seeds of cosmic structure. These fluctuations, though incredibly small, were crucial. As the universe continued to expand and cool, gravity began to pull matter together around these denser regions. Over billions of years, these seeds grew into the first stars, galaxies, and eventually the vast cosmic web we observe today. Without cosmic inflation, the universe might have remained a featureless void, devoid of the intricate structures that make it so fascinating. But cosmic inflation isn't just a theoretical idea. It's supported by evidence. One of the strongest pieces of evidence comes from the cosmic microwave background, the afterglow of the Big Bang. This faint radiation, which fills the entire universe, carries subtle patterns that match the predictions of inflation. These patterns, like a cosmic fingerprint, tell us that the universe underwent a period of rapid expansion early in its history. Yet, despite the evidence, cosmic inflation remains one of the most profound mysteries in cosmology. What triggered this rapid expansion? What caused it to stop? And what, if anything, existed before inflation began? These questions push the boundaries of our understanding, challenging us to rethink the very nature of space, time, and the origins of the universe. As we explore the cosmic dawn era, it's impossible to ignore the profound influence of cosmic inflation. This brief but transformative period laid the groundwork for the first structures in the universe, shaping the cosmic landscape we see today. It's a reminder that even the smallest fluctuations can have monumental consequences, echoing across billions of years to shape the destiny of the cosmos. Next, we'll turn our attention to the first binary star systems and their role in the early universe. How did these pairs of stars form, and what impact did they have on the evolution of galaxies? Stay with us as we uncover the secrets of the first binary stars. Now, let's shift our gaze to the first binary star systems, a fascinating chapter in the story of the early universe. Binary stars, pairs of stars orbiting a common center of mass, are incredibly common in the cosmos today. But how did these stellar duos form in the first place, and what role did they play in shaping the universe during the cosmic dawn era? The formation of the first binary stars likely began in the dense clouds of gas left over from the Big Bang. As gravity pulled matter together, these clouds fragmented into smaller clumps, each with the potential to collapse and ignite into a star. In some cases, these clumps didn't form single stars but instead split into two or more, giving birth to binary or even multiple star systems. This process was driven by the complex interplay of gravity, turbulence, and the cooling of gas, which allowed these clumps to break apart before fully collapsing into a single star. Once formed, binary stars had a profound impact on their surroundings. Their gravitational interactions could fling nearby stars and gas clouds out of their orbits, stirring up the early universe and influencing the formation of larger structures. Additionally, binary systems often produce powerful stellar winds and radiation, which can heat and ionize the surrounding gas, shaping the environment in which future stars and galaxies would form. But perhaps the most intriguing aspect of binary stars is their potential to create some of the most energetic events in the universe. When one star in a binary system exhausts its fuel and collapses into a neutron star or black hole, it can begin to siphon material from its companion. This process can lead to spectacular phenomena like X-ray bursts, supernova, and even the mergers of neutron stars or black holes, which we now know produce gravitational waves. These events not only enrich the cosmos with heavy elements, but also leave behind clues about the conditions of the early universe. The first binary stars were more than just cosmic curiosities. They were key players in the evolution of the early universe. By stirring up gas, triggering star formation, and producing explosive events, they helped shape the cosmic landscape we see today. Their legacy is a reminder that even the smallest systems can have an outsized impact on the universe's grand story. Next, we'll explore another cosmic mystery, the origin of cosmic dust. How did this essential ingredient for star formation first appear in the universe, and what role did it play in the birth of galaxies? Stay with us as we uncover the secrets of the first cosmic dust. Now, let's turn our attention to a seemingly humble yet vital ingredient in the cosmic recipe, cosmic dust. This fine, powdery material, often overlooked, is one of the unsung heroes of the universe. Without it, the formation of stars and galaxies as we know them might never have happened. But how did this essential component first appear in the universe, and what role did it play during the cosmic dawn era? Cosmic dust is made up of tiny solid particles, often just a fraction of a millimeter in size, composed of elements like carbon, silicon, and iron. These particles might seem insignificant, but they are anything but. They act as the building blocks for star formation, providing the necessary material for gas clouds to cool, condense, and eventually collapse into stars. But here's the mystery. In the early universe, shortly after the Big Bang, there was no dust. The cosmos was filled with only hydrogen, helium, and trace amounts of lithium. So, where did the dust come from? The answer lies in the life cycles of the first stars. When these massive stars reached the end of their lives, they didn't fade quietly. Instead, they exploded in spectacular supernova, scattering their enriched interiors across the cosmos. These explosions released not only heavy elements like carbon and oxygen, but also tiny solid particles, cosmic dust. Over time, this dust mixed with the surrounding gas, creating the perfect conditions for the next generation of stars to form. But the story doesn't end there. Cosmic dust also played a crucial role in cooling the early universe. As gas clouds mixed with dust, the particles absorbed heat and radiated it away, allowing the gas to cool and collapse more efficiently. This cooling effect was essential for the formation of smaller, more stable stars, as well as the first galaxies. Without dust, the universe might have remained a hot, chaotic place, unable to give rise to the structures we see today. Interestingly, cosmic dust also acted as a cosmic time capsule, preserving the chemical fingerprints of the first stars. By studying ancient dust grains found in meteorites or observed in distant galaxies, scientists can piece together the history of star formation and the evolution of the early universe. These tiny particles hold clues to some of the biggest questions in astrophysics, from the origins of heavy elements to the processes that shaped the first galaxies. The mystery of cosmic dust is a reminder that even the smallest components of the universe can have a profound impact. From triggering star formation to cooling the early cosmos, dust played a pivotal role in shaping the universe during the cosmic dawn era. Its story is a testament to the interconnectedness of all things in the cosmos, from the tiniest particles to the grandest galaxies. Next, we'll dive into another cosmic enigma, the formation of the first active galactic nuclei. What powered these incredibly bright objects, and what do they reveal about the early universe? Stay with us as we explore the secrets of the first active galactic nuclei. Now, let's shift our gaze to one of the most dazzling phenomena in the cosmos, active galactic nuclei. These incredibly bright objects, often outshining entire galaxies, are powered by supermassive black holes at their centers. But how did these colossal black holes form so early in the universe? And what can they tell us about the conditions of the cosmic dawn era? Active galactic nuclei, or AN, are like cosmic lighthouses, beaming intense radiation across the universe. At their heart lies a supermassive black hole, millions or even billions of times more massive than our Sun. As matter spirals into these black holes, it heats up and emits enormous amounts of energy, creating some of the brightest objects we can observe. But here's the puzzle. How did these supermassive black holes grow so massive so quickly after the Big Bang? One leading theory suggests that the first supermassive black holes formed through a process called direct collapse. In this scenario, massive clouds of gas in the early universe collapsed directly into black holes without first forming stars. These black holes then grew rapidly by devouring surrounding gas and merging with other black holes. Another possibility is that they started as smaller black holes, remnants of the first stars, and grew over time through accretion and mergers. Regardless of how they formed, their existence challenges our understanding of the early universe's timeline. The light from these active galactic nuclei provides a unique window into the past. By studying their spectra, scientists can determine the composition of the gas surrounding them and the conditions in which they formed. For example, the presence of heavy elements like carbon and oxygen in the gas suggests that these black holes formed in environments already enriched by earlier generations of stars. This gives us clues about the timeline of star formation and the chemical evolution of the early universe. Interestingly, active galactic nuclei also played a role in shaping their surroundings. The intense radiation they emitted could ionize gas, preventing it from cooling and collapsing into new stars. This feedback mechanism may have regulated the growth of galaxies, influencing how they evolved over time. In some cases, the energy from AGNs could even blow gas out of galaxies entirely, halting star formation and leaving behind red and dead galaxies with little to no new stellar activity. The study of active galactic nuclei also raises intriguing questions about the relationship between black holes and their host galaxies. Observations show that the mass of a galaxy's central black hole is often proportional to the mass of its stellar bulge. This suggests a deep connection between the growth of black holes and the formation of galaxies, though the exact nature of this relationship remains a mystery. Did black holes drive galaxy formation, or did galaxies shape the growth of black holes? Or is it a combination of both? As we continue to explore the first active galactic nuclei, we uncover not only the secrets of these luminous objects, but also the broader story of how the universe evolved. Their formation and behavior provide critical insights into the conditions of the early universe, from the growth of supermassive black holes to the interplay between galaxies and their central engines. Next, we'll turn our attention to another cosmic mystery, the nature of the first light in the universe. What was this light like, and how did it transition from being absorbed by gas to illuminating the cosmos? Join us as we unravel the story of the universe's earliest glow. Now, let's journey back to the very beginning, to a time when the universe was cloaked in darkness. This is the story of the first light, the moment when the cosmos began to glow, breaking free from the shadows of the cosmic dark ages. But what exactly was this light, and how did it emerge to illuminate the universe? The first light in the universe didn't come from stars or galaxies. Instead, it originated from the hot, dense plasma that filled the early universe shortly after the Big Bang. This light, known as the cosmic microwave background, was initially trapped within the opaque fog of ionized gas. Photons, or particles of light, couldn't travel far without colliding with free electrons scattering in all directions. The universe was a glowing, chaotic soup of energy and matter, but it was far from transparent. Then, something extraordinary happened. As the universe expanded and cooled, electrons and protons began to combine, forming neutral hydrogen atoms. This process, called recombination, occurred around 380,000 years after the Big Bang. for the first time, photons could travel freely through space without being constantly scattered. The universe became transparent, and the first light was finally able to shine through. This light, now stretched and cooled by the expansion of the universe, is what we detect today as the cosmic microwave background. But the story doesn't end there. After recombination, the universe entered a period known as the cosmic dark ages, where no new sources of light existed. The first stars and galaxies had yet to form, and the universe was filled with neutral hydrogen gas. This gas absorbed the faint ultraviolet light emitted by the first stars and galaxies, preventing it from traveling far. It wasn't until the epoch of reionization, hundreds of millions of years later, that this gas became ionized once again, allowing light to travel freely and illuminate the cosmos. The transition from a dark, neutral universe to one filled with light is one of the most profound mysteries of the cosmic dawn era. What caused the gas to reionize? Was it the intense radiation from the first stars, the powerful jets from active galactic nuclei, or a combination of both? And how did this process shape the large-scale structure of the universe, influencing the formation of galaxies and the distribution of matter? The first light not only marks the dawn of the universe's visibility, but also serves as a crucial tool for astronomers. By studying the cosmic microwave background, we can peer back in time to the moment when the universe became transparent. This ancient light carries imprints of the early universe's conditions, revealing details about its density, temperature, and composition. It's like a cosmic fingerprint, offering clues about the universe's infancy and the forces that shaped its evolution. As we unravel the mystery of the first light, we gain a deeper understanding of how the universe transformed from a dark, featureless expanse into the vibrant, luminous cosmos we see today. This light, born in the aftermath of the Big Bang, continues to guide our exploration of the universe's origins, illuminating the path to uncovering its deepest secrets. Next, we'll explore the formation of the first star-forming regions, the cosmic nurseries where the earliest stars were born. What made these regions unique, and how did they set the stage for the birth of galaxies? Join us as we delve into the heart of the universe's earliest stellar factories. Now, let's turn our attention to the cosmic nurseries where the universe's first stars were born, the first star-forming regions. These regions were the birthplaces of the earliest stars, setting the stage for the formation of galaxies and the large-scale structure of the universe. But what made these primordial star-forming regions so unique, and how did they differ from the stellar nurseries we see today? The first star-forming regions emerged from the dense pockets of gas that began to collapse under their own gravity, hundreds of millions of years after the Big Bang. Unlike later star-forming regions, which are enriched with heavy elements like carbon and oxygen, these early regions were composed almost entirely of hydrogen and helium. This lack of heavier elements, or metals, as astronomers call them, had a profound impact on how stars formed. Without metals, the gas couldn't cool as efficiently, leading to the formation of much larger and hotter stars than those we observe in the modern universe. These first stars, known as population 3 stars, were true cosmic giants, some reaching masses hundreds of times greater than our Sun. Their immense size and brightness meant they lived fast and died young, exploding as supernovae within just a few million years. These explosions not only scattered the first heavy elements into the surrounding gas, but also created shock waves that triggered further star formation in nearby regions. This cycle of star birth and death played a crucial role in shaping the early universe, seeding it with the raw materials needed for future generations of stars and galaxies. Another key difference was the environment in which these first star-forming regions existed. The early universe was much denser and hotter than it is today, with galaxies and large-scale structures still in their infancy. This meant that the first star-forming regions were often isolated, forming in the densest clumps of gas within the cosmic web. Over time, as the universe expanded and structures grew, star-forming regions became more interconnected, influenced by the gravitational pull of nearby galaxies and the feedback from supernova and black holes. The first star-forming regions also lacked the complex chemistry we see in modern stellar nurseries. Today, star-forming regions are rich with molecules like carbon monoxide and water, which help cool the gas and allow it to fragment into smaller clumps, leading to the formation of smaller stars. In contrast, the first star-forming regions relied on molecular hydrogen, the simplest molecule, to cool the gas. This limited cooling mechanism meant that the first stars tended to form in larger, more massive clumps, resulting in fewer but more massive stars. Understanding these first star-forming regions is like uncovering the blueprint of the universe's earliest structures. They were the cosmic laboratories where the first stars ignited, lighting up the darkness and setting the universe on a path toward complexity and diversity. By studying these regions, astronomers can piece together how the first stars and galaxies formed and how they influenced the evolution of the cosmos. As we continue our journey through the mysteries of the cosmic dawn era, we'll next explore the peculiar shapes of the first galaxies and how they evolved into the structured galaxies we see today. What forces shaped these early galaxies, and why did they look so different from their modern counterparts? Stay with us as we unravel another piece of the cosmic puzzle. Now, let's shift our gaze to the peculiar shapes of the first galaxies and uncover why they looked so different from the majestic spirals and ellipticals we see today. The early universe was a chaotic place, and the first galaxies were no exception. Unlike the well-defined, symmetrical shapes of modern galaxies, the first galaxies were irregular, clumpy, and often resembled cosmic blobs more than the structured systems we're familiar with. But what caused these early galaxies to take on such unusual forms, and how did they transform over time? One of the key factors behind the irregular shapes of the first galaxies was the environment in which they formed. The early universe was a turbulent, high-energy place filled with dense pockets of gas and dark matter. As these clumps of matter collapsed under gravity, they began to form the first galaxies. However, without the stabilizing influence of heavier elements or metals, the gas in these early galaxies couldn't cool efficiently. This led to chaotic, uneven star formation, with stars and gas clumping together in irregular patterns rather than settling into orderly disks or spheres. Another factor was the lack of rotational stability in these early galaxies. In modern galaxies, rotation plays a crucial role in shaping their structure. As gas and stars orbit a galaxy's center, centrifugal force flattens the material into a disk, creating the familiar spiral arms we see in galaxies like the Milky Way. But in the first galaxies, rotation was often weak or disorganized. Without a strong rotational force to organize the material, these galaxies remained lumpy and asymmetrical. The first galaxies were also heavily influenced by frequent collisions and mergers. In the early universe, galaxies were much closer together than they are today, and gravitational interactions were common. When two galaxies collided, their irregular shapes became even more distorted, with streams of gas and stars being pulled in all directions. These chaotic mergers prevented the galaxies from settling into stable, structured forms, instead leaving them as messy, clumpy systems. Over time, however, these irregular galaxies began to evolve. As the universe expanded and galaxies grew farther apart, collisions became less frequent. At the same time, the enrichment of heavy elements from supernova allowed gas to cool more efficiently, enabling smoother, more organized star formation. Rotation also became more pronounced as galaxies grew larger, helping to flatten them into disks. Gradually, the chaotic blobs of the early universe transformed into the structured spirals and ellipticals we see today. But the story doesn't end there. Even today, some galaxies retain traces of their irregular origins, Dwarf galaxies, for example, often have irregular shapes, reflecting the turbulent conditions of the early universe. By studying these galaxies, astronomers can gain insights into the processes that shaped the first galaxies and how they evolved over billions of years. As we continue to explore the mysteries of the cosmic dawn era, we'll next delve into the role of the first intergalactic gas and how it influenced the formation of galaxies. How did this gas shape the early universe, and what clues does it hold about the origins of cosmic structure? Stay with us as we uncover another layer of the cosmic story. Now, let's turn our attention to the vast, invisible ocean that filled the early universe, the first intergalactic gas. This gas, primarily composed of hydrogen and helium, played a crucial role in shaping the cosmos as we know it. But what exactly was this gas like, and how did it influence the formation of the first galaxies? The first intergalactic gas was spread unevenly across the universe, forming a complex web of filaments and voids. These filaments, often referred to as the cosmic web, were the scaffolding upon which galaxies would later form. Dense regions within this web acted as the birthplaces of the first stars and galaxies, while the voids remained largely empty. This uneven distribution of gas created a patchwork of high-density and low-density regions, setting the stage for the formation of cosmic structures. One of the most fascinating properties of this early intergalactic gas was its temperature. Initially, the gas was incredibly hot, heated by the energy released during the Big Bang. However, as the universe expanded and cooled, so did the gas. By the time the first stars began to form, the gas had cooled enough to allow gravity to pull it into dense clumps, which eventually collapsed to form stars and galaxies. This cooling process was essential for the formation of the first structures, as it allowed the gas to condense and ignite the first bursts of star formation. But the intergalactic gas wasn't just a passive player in the cosmic drama. It also acted as a reservoir of material for the growing galaxies. As galaxies formed, they drew in gas from their surroundings, fueling further star formation. This process, known as accretion, was critical for the growth and evolution of galaxies. Without a steady supply of intergalactic gas, galaxies would have quickly exhausted their fuel and ceased to form new stars. The intergalactic gas also played a key role in the process of reionization. As the first stars and galaxies formed, they emitted intense ultraviolet radiation which ionized the surrounding gas. This ionized gas then spread throughout the intergalactic medium, gradually transforming the universe from a neutral state to one filled with ionized gas. This process, known as the epoch of reionization, was a pivotal moment in the history of the universe, and the intergalactic gas was at the heart of it. Interestingly, the intergalactic gas also left behind clues about the early universe. By studying the absorption lines in the spectra of distant quasars, astronomers can trace the distribution and properties of this ancient gas. These observations reveal a wealth of information about the conditions of the early universe, including the density, temperature, and chemical composition of the gas. Through these studies, we can piece together the story of how the first galaxies formed and evolved. As we continue to explore the mysteries of the cosmic dawn era, we'll next investigate the possibility of supermassive stars in the early universe. Could stars hundreds of times more massive than the Sun have existed during this time? And what impact would they have had on the cosmos? Stay with us as we uncover another fascinating chapter in the story of the universe's beginnings. Now, let's shift our gaze to one of the most intriguing possibilities of the cosmic dawn era, the existence of supermassive stars. Imagine stars so colossal that they dwarf our Sun by hundreds of times in mass. Could such titans have burned brightly in the early universe? And if so, what role did they play in shaping the cosmos? The idea of supermassive stars isn't just a flight of fancy. It's grounded in theoretical models that suggest these behemoths could have formed in the dense, pristine environments of the early universe. Unlike the stars we see today, which form from gas clouds enriched with heavier elements, the first stars were born from pure hydrogen and helium. This lack of heavier elements meant that these stars could grow to extraordinary sizes before collapsing under their own gravity. Some theories propose that these supermassive stars could have reached masses up to 1,000 times that of our Sun, burning fiercely and living short, explosive lives. But why haven't we directly observed these supermassive stars? The answer lies in their fleeting existence. Stars of such immense size burn through their fuel at an astonishing rate, leading to lifespans that are mere millions of years, a blink of an eye in cosmic terms. By the time light from these stars could reach us, they would have long since vanished, leaving behind only traces of their existence. However, their impact on the universe would have been profound. One of the most significant contributions of these supermassive stars would have been their role in seeding the cosmos with heavy elements. When these stars reached the end of their lives, they likely exploded in cataclysmic events known as pair instability supernova. These explosions would have scattered elements like carbon, oxygen, and iron into the surrounding gas, enriching it and paving the way for the formation of future generations of stars and planets. Without these early giants, the universe might have remained a barren expanse of hydrogen and helium. Another fascinating aspect of supermassive stars is their potential influence on the formation of the first black holes. Some models suggest that the cores of these stars could have collapsed directly into black holes, bypassing the typical supernova stage. These black holes, born from the remnants of supermassive stars, might have served as the seeds for the supermassive black holes we observe at the centers of galaxies today. This connection between the first stars and the first black holes offers a tantalizing glimpse into how the universe's largest structures might have formed. Yet, the mystery of supermassive stars remains unsolved. While simulations and theoretical models support their existence, direct evidence is elusive. Astronomers continue to search for clues in the faint echoes of the early universe, hoping to uncover signs of these colossal stars. Observations of distant quasars and the chemical composition of ancient stars may hold the key to unraveling this cosmic puzzle. As we ponder the possibility of these stellar giants, we're reminded of how much we still have to learn about the cosmic dawn era. Next, we'll explore the nature of the first cosmic explosions and how they shaped the early universe. What were these explosions like, and what legacy did they leave behind? Stay with us as we continue our journey through the mysteries of the cosmos. Now, let's turn our attention to the first cosmic explosions, events so powerful they reshaped the fabric of the early universe. These explosions, known as pair instability supernova, were unlike anything we see today. Born from the deaths of the first supermassive stars, these cataclysmic events were not just spectacular displays of energy, they were the architects of the cosmos as we know it. Pair instability supernova occur when a star becomes so massive that the heat in its core triggers a runaway reaction. Instead of collapsing into a black hole or neutron star, the star's core becomes so hot that it produces pairs of electrons and positrons. This process destabilizes the star, leading to a violent explosion that completely obliterates it, leaving no remnant behind. These explosions were hundreds of times more energetic than typical supernova, releasing enough light to outshine entire galaxies. The impact of these explosions on the early universe was profound. For one, they were responsible for seeding the cosmos with the first heavy elements. Elements like carbon, oxygen, and iron, which are essential for life as we know it, were forged in the hearts of these massive stars and scattered across the universe by their explosive deaths. Without these early cosmic furnaces, the universe would have remained a sea of hydrogen and helium, devoid of the building blocks needed for planets, stars, and even life itself. But the influence of these explosions didn't stop there. The shockwaves from pair instability supernova also played a crucial role in shaping the structure of the early universe. As these shockwaves rippled through the surrounding gas, they compressed it, triggering the formation of new stars and galaxies. In a sense, these explosions acted as cosmic sculptors, carving out the first large-scale structures in the universe and setting the stage for the cosmic web we see today. Interestingly, the remnants of these explosions might still be detectable in the universe today. Astronomers have been searching for the chemical fingerprints of pair instability supernova in the spectra of ancient stars. These stars, formed from the enriched gas left behind by the first explosions, carry traces of the elements produced in those early events. By studying these ancient stars, scientists hope to piece together the story of the first cosmic explosions and their role in shaping the universe. Yet, despite their importance, pair instability supernova remain shrouded in mystery. Because they occurred so early in the universe's history, their light has long since faded, leaving only indirect clues for us to decipher. Simulations and theoretical models provide glimpses into their nature, but direct evidence is still elusive. As we continue to explore the distant reaches of the cosmos, we may one day uncover the remnants of these titanic explosions, shedding light on one of the most dramatic chapters in the universe's history. As we reflect on the legacy of these first cosmic explosions, we're reminded of how interconnected the universe truly is. From the birth of the first stars to the formation of galaxies, every event has left its mark on the cosmos. Next, we'll delve into the mystery of magnetic monopoles and whether these hypothetical particles played a role in the cosmic dawn era. What are magnetic monopoles and why do they remain one of the most elusive puzzles in physics? Stay with us as we continue to unravel the mysteries of the early universe. Now, let's shift our focus to one of the most intriguing and elusive mysteries of the cosmic dawn era, the possibility of magnetic monopoles. These hypothetical particles, which possess only a single magnetic pole, either north or south, have long fascinated physicists and cosmologists alike. Unlike the magnets we're familiar with, which always have two poles, magnetic monopoles challenge our fundamental understanding of electromagnetism and the forces that govern the universe. The concept of magnetic monopoles arises from certain theories in physics, particularly those attempting to unify the forces of nature. In the early universe during the cosmic dawn era, conditions were extreme enough that such particles might have formed. If they existed, magnetic monopoles could have played a significant role in shaping the magnetic fields that permeate the cosmos today. But here's the catch: despite decades of searching, no one has ever detected a magnetic monopole. This absence has led to one of the most puzzling questions in modern physics. Did magnetic monopoles ever exist, or are they purely theoretical? One reason magnetic monopoles are so hard to find is that they are predicted to be incredibly rare. If they were produced during the cosmic dawn era, they would have been diluted as the universe expanded, making them nearly impossible to detect today. Some theories suggest that these particles could have been created during phase transitions in the early universe, moments when the fundamental forces separated from one another. These transitions might have left behind defects in spacetime, giving rise to magnetic monopoles. However, without direct evidence, this remains speculative. The search for magnetic monopoles isn't just an academic exercise. If they exist, they could provide crucial insights into the nature of the universe's earliest moments. For instance, their presence would support grand unified theories, which attempt to describe how the fundamental forces of nature were once combined into a single force. Additionally, magnetic monopoles could help explain the origin of cosmic magnetic fields, which are observed throughout the universe but whose origins remain unclear. Despite the lack of direct evidence, scientists haven't given up on the hunt. Experiments using advanced particle detectors and even cosmic ray observatories have been designed to search for these elusive particles. Some researchers have even proposed that magnetic monopoles could be hiding in unexpected places, such as within the cores of neutron stars or trapped in the Earth's magnetic field. While these ideas are still in the realm of theory, they highlight the creativity and determination of scientists in their quest to solve this cosmic mystery. As we ponder the existence of magnetic monopoles, we're reminded of how much we still have to learn about the early universe. Their discovery would not only revolutionize our understanding of physics, but also shed light on the conditions that prevailed during the cosmic dawn era. Next, we'll explore another fascinating phenomenon, the first cosmic jets. How did these powerful streams of particles form, and what role did they play in shaping the early universe? Stay with us as we continue our journey through the mysteries of the cosmic dawn. Now, let's turn our attention to another awe-inspiring phenomenon of the cosmic dawn era, the first cosmic jets. These powerful streams of particles traveling at nearly the speed of light are among the most energetic features in the universe. But how did they form, and what impact did they have on the early cosmos? Cosmic jets are typically associated with some of the most extreme objects in the universe, black holes and neutron stars. When matter falls into a black hole or spirals around a neutron star, it doesn't just disappear quietly. Instead, it gets heated to incredible temperatures, creating intense magnetic fields and launching jets of particles into space. These jets can stretch for thousands, even millions of light years, carving out vast regions of influence in their surroundings. During the cosmic dawn era, the first cosmic jets likely emerged from the earliest supermassive black holes and neutron stars. These objects, born from the collapse of massive stars or through other mechanisms, would have been surrounded by dense clouds of gas and dust. As material fell into these objects, the immense gravitational energy was converted into radiation and kinetic energy, powering the jets. These jets, in turn, would have blasted through the surrounding gas, heating it up and preventing it from collapsing to form new stars. But the influence of cosmic jets didn't stop there. They also played a crucial role in shaping the large-scale structure of the universe. By pushing gas and dust out of their way, jets created bubbles of hot, ionized gas that expanded into the surrounding medium. These bubbles acted like cosmic bulldozers, clearing paths through the early universe and influencing where and how galaxies could form. In some cases, jets may have even triggered star formation by compressing gas in their wake, creating pockets of dense material that eventually collapsed into stars. One of the most fascinating aspects of cosmic jets is their ability to transport energy over vast distances. The particles in these jets are accelerated to such high speeds that they can travel across entire galaxies, depositing energy far from their source. This energy transfer could have had profound effects on the evolution of the early universe, from regulating the growth of galaxies to influencing the distribution of matter on the largest scales. Despite their importance, many questions about the first cosmic jets remain unanswered. For instance, how exactly were these jets launched? What mechanisms allowed them to remain collimated, focused into narrow beams over such enormous distances? And how did they interact with the surrounding gas and dark matter? These are just some of the mysteries that scientists are working to unravel as they study the remnants of these ancient jets in the modern universe. As we explore the legacy of the first cosmic jets, we gain a deeper appreciation for the dynamic and interconnected nature of the early cosmos. These jets were not just spectacular displays of energy, they were key players in shaping the universe as we know it today. Next, we'll delve into another captivating mystery, the formation of the first dark matter halos. How did these invisible structures come to be, and why are they so crucial to our understanding of the universe's evolution? Stay with us as we continue our journey through the mysteries of the cosmic dawn. Now, let's shift our focus to one of the most enigmatic components of the cosmic dawn era, the first dark matter halos. These invisible structures are the backbone of the universe's large-scale architecture, yet their origins and role in the early cosmos remain shrouded in mystery. Dark matter, which makes up about 85% of the universe's total matter, doesn't interact with light or ordinary matter in the way we're familiar with. Instead, it exerts its influence through gravity, shaping the distribution of galaxies and other cosmic structures. During the cosmic dawn era, the first dark matter halos began to form, acting as gravitational wells that pulled in gas and dust, setting the stage for the birth of the first stars and galaxies. But how did these halos come into existence? In the early universe, tiny fluctuations in the density of dark matter, seeded by quantum processes during the Big Bang, began to grow. Over time, gravity amplified these fluctuations, causing denser regions to collapse and form halos. These halos served as the scaffolding for the first structures in the universe, providing the gravitational pull needed to gather gas and ignite the first stars. The role of dark matter halos didn't end there. They also played a critical part in the formation of galaxies. As gas fell into these halos, it cooled and condensed, eventually forming stars and galaxies. Without dark matter halos, the universe would have remained a diffuse, featureless expanse, devoid of the intricate structures we see today. One of the most intriguing aspects of dark matter halos is their distribution. They aren't scattered randomly, but instead form a cosmic web, a vast network of filaments and nodes that connect galaxies across the universe. This web-like structure, which began to take shape during the cosmic dawn era, is a direct result of the gravitational influence of dark matter halos. Despite their importance, many questions about the first dark matter halos remain unanswered. For instance, what determined their size and mass? How did they interact with the surrounding gas and radiation? And how did they evolve over time to become the massive structures we observe today? These are just some of the puzzles that scientists are working to solve as they study the remnants of these ancient halos in the modern universe. Understanding the first dark matter halos is crucial, not only for piecing together the story of the cosmic dawn, but also for unraveling the broader mysteries of the universe's evolution. These invisible structures are the hidden architects of the cosmos, shaping everything from the smallest galaxies to the largest superclusters. As we continue our journey through the mysteries of the cosmic dawn era, we'll next explore another fascinating phenomenon, the formation of the first cosmic filaments. How did these threads of gas and dark matter weave together to create the cosmic web? Stay with us as we uncover more secrets of the early universe. Now, let's unravel another fascinating thread in the tapestry of the cosmic dawn era, the first cosmic filaments. These delicate, thread-like structures are the invisible highways of the universe, weaving together galaxies and clusters into the vast cosmic web we observe today. But how did these filaments form, and what role did they play in shaping the early universe? To understand cosmic filaments, we need to go back to the very beginning. In the aftermath of the Big Bang, the universe was a nearly uniform sea of matter and energy. However, tiny fluctuations in density, imprinted during the universe's rapid expansion, began to grow under the influence of gravity. These fluctuations acted as seeds, with denser regions pulling in more matter over time. As dark matter halos formed and grew, they began to connect through these filaments, creating a network that spanned the cosmos. These filaments are made up of both dark matter and gas, with the dark matter providing the gravitational framework and the gas flowing along these pathways. As the gas moved through the filaments, it cooled and condensed, eventually forming stars and galaxies at the intersections where filaments met. This process gave rise to the first large-scale structures in the universe, transforming it from a featureless expanse into a complex, interconnected web. One of the most remarkable aspects of cosmic filaments is their sheer scale. Stretching across billions of light years, they form the backbone of the cosmic web, connecting galaxies and clusters like beads on a string. Yet, despite their immense size, filaments are incredibly thin, often just a few million light years across. This delicate balance between scale and structure makes them one of the most intriguing features of the early universe. But how did these filaments maintain their shape and stability? The answer lies in the interplay between gravity and the pressure of the gas flowing through them. Gravity pulls matter into the filaments while the gas pressure resists collapse, creating a dynamic equilibrium that allows filaments to persist over cosmic timescales. This balance also plays a crucial role in regulating the flow of gas into galaxies, influencing their growth and evolution. The study of cosmic filaments is not just about understanding the past, it also sheds light on the present and future of the universe. By mapping these structures, astronomers can trace the distribution of dark matter and gas, uncovering clues about the universe's evolution and the forces that shape it. Filaments also serve as cosmic highways, guiding the movement of galaxies and influencing their interactions over billions of years. As we continue to explore the mysteries of the cosmic dawn era, the formation of cosmic filaments stands as a testament to the intricate and interconnected nature of the universe. These threads of gas and dark matter are more than just relics of the past, they are the foundation upon which the cosmos is built. Next, we'll delve into another captivating mystery, the possibility of starless galaxies during this era. What could these ghostly structures reveal about the early universe? Stay with us as we uncover more secrets of the cosmic dawn. Now, let's turn our attention to a truly enigmatic possibility, the existence of starless galaxies during the cosmic dawn era. Imagine a galaxy without stars, a vast expanse of gas and dark matter drifting silently through the early universe. Could such ghostly structures have existed? And if so, what might they tell us about the formation of the first galaxies? The idea of starless galaxies challenges our understanding of how galaxies form. Typically, galaxies are thought to begin as clouds of gas that collapse under gravity, eventually igniting stars. But what if, in some regions of the early universe, this process was interrupted? Perhaps the gas was too diffuse, or the conditions weren't quite right for star formation to take hold. In these cases, galaxies might have remained dark, composed solely of gas and dark matter, with no stars to light them up. One intriguing theory suggests that starless galaxies could have formed in regions where the gas was too hot or turbulent to cool and condense into stars. Without the cooling needed to trigger star formation, these galaxies would have remained in a kind of cosmic limbo, invisible to our telescopes. Another possibility is that starless galaxies were simply too small or isolated to gather enough gas to form stars, leaving them as faint, starless shadows in the cosmos. Detecting these elusive structures is no easy task. Without stars, they emit no visible light, making them nearly impossible to observe directly. However, astronomers have developed clever ways to search for them. By studying the gravitational effects of dark matter, or by looking for faint traces of gas in the early universe, scientists hope to uncover evidence of these ghostly galaxies. Some even speculate that starless galaxies could be the missing link in our understanding of how the first galaxies formed, providing clues about the conditions that allowed stars to ignite. If starless galaxies did exist, they could have played a crucial role in the evolution of the early universe. They might have served as reservoirs of gas, feeding the growth of nearby galaxies and influencing the formation of the cosmic web. Alternatively, they could have been the precursors to the first galaxies, their gas eventually cooling and collapsing to form the stars we see today. Either way, their existence would reshape our understanding of the cosmic dawn era. As we continue to explore the mysteries of this pivotal time in the universe's history, the possibility of starless galaxies reminds us just how much we have yet to discover. These ghostly structures, if they existed, could hold the key to unlocking some of the deepest secrets of the cosmos. Next, we'll dive into another captivating mystery, the objects responsible for reionizing the universe. What cosmic forces could have driven this monumental transformation? Stay with us as we uncover more secrets of the cosmic dawn. Now, let's shift our focus to one of the most transformative events in the history of the universe, the epoch of reionization. This was the period when the cosmos transitioned from a dark, neutral state to one filled with ionized gas, and it raises a fascinating question. What cosmic objects were responsible for driving this monumental change? The leading candidates for the first cosmic reionizers are quasars and galaxies. Quasars, the brightest objects in the universe, are powered by supermassive black holes at their centers. These black holes devour surrounding matter, releasing enormous amounts of energy in the form of radiation. This intense radiation could have ionized the surrounding gas, stripping electrons from atoms and lighting up the universe. Quasars are thought to have been particularly active during the cosmic dawn era, making them strong contenders for the role of reionizers. But quasars weren't the only players in this cosmic drama. The first galaxies, too, likely played a significant part. These early galaxies were filled with young, massive stars that emitted powerful ultraviolet light. This light, much like the radiation from quasars, could have ionized the gas around them, creating bubbles of ionized material that expanded and merged over time. As more stars formed and more galaxies emerged, these bubbles grew larger, eventually filling the universe with ionized gas. The challenge for astronomers is determining which of these objects, quasars or galaxies, played the dominant role. Some theories suggest that quasars were the primary drivers, given their immense energy output. Others argue that galaxies, with their vast numbers of stars, collectively contributed more to the reionization process. It's also possible that both quasars and galaxies worked together, each playing a crucial part in this cosmic transformation. To unravel this mystery, scientists study the light from distant quasars and galaxies, looking for clues about how they interacted with the gas around them. By analyzing the absorption lines in quasar spectra, known as the Lyman alpha forest, researchers can map the distribution of ionized gas and trace its origins. Similarly, observations of early galaxies provide insights into their star formation rates and the amount of ultraviolet light they emitted. Understanding the first cosmic reionizers isn't just about solving a historical puzzle. It's about piecing together the story of how the universe evolved into the vibrant, ionized state we see today. These objects didn't just light up the cosmos, they shaped the conditions that allowed galaxies, stars, and eventually planets to form. As we continue to explore this pivotal era, we're reminded of the intricate interplay of forces that have shaped the universe over billions of years. Next, we'll explore another fascinating aspect of the cosmic dawn era, the formation of the first cosmic bubbles. How did these bubbles of ionized gas emerge, and what role did they play in the evolution of the early universe? Stay with us as we uncover more secrets of this extraordinary time. Now, let's turn our attention to one of the most intriguing phenomena of the cosmic dawn era, the formation of the first cosmic bubbles. These bubbles, made up of ionized gas, were like glowing pockets scattered throughout the early universe, and their emergence marked a critical step in the evolution of the cosmos. But how did these bubbles form, and what role did they play in shaping the universe as we know it? The story begins with the first stars and galaxies. As these early objects ignited, they emitted intense ultraviolet light, which had enough energy to strip electrons from the surrounding hydrogen atoms. This process, known as ionization, created regions of ionized gas around the stars and galaxies. Over time, these regions expanded outward, forming bubbles of ionized material. Think of it like a campfire lighting up the darkness, except in this case, the fire was a star, and the darkness was the vast, neutral gas filling the early universe. These bubbles didn't just sit still, they grew. As more stars formed and more galaxies emerged, their combined ultraviolet radiation pushed the boundaries of the bubbles further out. The bubbles began to overlap and merge, creating larger and larger regions of ionized gas. This expansion was a key part of the epoch of reionization, the period when the universe transitioned from being mostly neutral to mostly ionized. But here's where things get even more fascinating. The growth of these bubbles wasn't uniform. Some regions of the universe had more stars and galaxies, so their bubbles grew faster and larger. Other areas with fewer stars lagged behind. This uneven growth created a patchwork of ionized and neutral gas, like a cosmic quilt stitched together by the light of the first stars. Scientists study these bubbles by looking at the light from distant quasars. As this light passes through the early universe, it interacts with the gas, leaving behind absorption lines in the quasar spectrum. These lines, known as the Lyman alpha forest, act like a fingerprint, revealing the distribution of ionized and neutral gas. By analyzing these patterns, researchers can map the size and shape of the bubbles, piecing together how they formed and expanded. The first cosmic bubbles weren't just a byproduct of star formation. They were a driving force in the evolution of the universe. By ionizing the gas around them, they cleared the way for light to travel freely, ending the cosmic dark ages and ushering in a new era of transparency. They also influenced the formation of future galaxies, as the ionized gas provided the raw material for new stars and structures to emerge. As we continue to explore the mysteries of the cosmic dawn era, these bubbles remind us of the delicate balance between light and matter, and how the smallest changes can have profound effects on the universe. Next, we'll dive into another captivating aspect of this era, the first cosmic winds. What were these winds and how did they shape the early universe? Stay tuned as we uncover more secrets of this extraordinary time. Now, let's shift our focus to another fascinating force that shaped the early universe, the first cosmic winds. These winds weren't like the gentle breezes we experience on Earth. Instead, they were powerful streams of gas and energy, driven by some of the most violent events in the cosmos, supernova and black holes. But how did these winds form, and what impact did they have on the universe during the cosmic dawn era? The story begins with the first stars. When these massive stars reached the end of their lives, they didn't fade quietly. They exploded in spectacular supernova. These explosions released enormous amounts of energy, blasting gas and heavy elements into space at incredible speeds. This material didn't just drift aimlessly. It was propelled outward, creating shock waves that pushed surrounding gas and dust ahead of them. These shockwaves acted like cosmic winds, sweeping through the early universe and reshaping the environment around them. But supernovae weren't the only drivers of these winds. Black holes, particularly those at the centers of early galaxies, also played a crucial role. As matter fell into these black holes, it didn't just disappear. It was heated to extreme temperatures and ejected in powerful jets. These jets, combined with radiation from the black holes, pushed gas outward, creating even more cosmic winds. Together, supernova and black holes acted like cosmic bellows, blowing gas and energy across vast distances. These winds didn't just move material around, they had a profound effect on the early universe. For one, they helped distribute heavy elements like carbon and oxygen, which were forged in the hearts of stars and scattered by supernova. These elements, essential for the formation of planets and life, were carried far and wide by the winds, enriching the cosmos with the building blocks of future worlds. The winds also influenced the formation of galaxies. By pushing gas outward, they could either trigger new star formation in some regions or suppress it in others. In areas where the winds compressed gas, they created dense pockets that collapsed to form new stars and galaxies. In other regions, the winds blew gas away, leaving behind voids where star formation was stifled. This dynamic interplay between creation and destruction helped shape the large-scale structure of the universe. Scientists study these ancient winds by observing distant galaxies and quasars. The light from these objects carries clues about the gas they've passed through, revealing the presence and effects of cosmic winds. By analyzing these signals, researchers can piece together how these winds influenced the growth and evolution of the early universe. The first cosmic winds were more than just a byproduct of violent cosmic events. They were a driving force in the universe's development. They carried the seeds of future stars and galaxies, sculpted the cosmic landscape, and set the stage for the rich, diverse universe we see today. As we continue to explore the mysteries of the cosmic dawn era, These winds remind us of the incredible power and complexity of the forces that shaped our cosmic home. Next, we'll delve into another captivating mystery, the first cosmic collisions. What happened when galaxies and black holes collided in the early universe, and how did these events shape the cosmos? Stay tuned as we uncover more secrets of this extraordinary era. Now, let's turn our attention to one of the most dramatic events in the early universe, the first cosmic collisions. Imagine two galaxies, each filled with stars, gas, and dark matter, hurtling toward each other at incredible speeds. When they finally meet, the result is nothing short of spectacular. These collisions weren't just chaotic crashes, they were transformative events that played a key role in shaping the cosmos as we know it today. The first collisions between galaxies were unlike anything we see in the modern universe. Back then, galaxies were smaller, denser, and packed closer together, making encounters far more frequent. When two galaxies collided, their stars didn't actually crash into each other. Space is so vast that stars rarely collide. Instead, the galaxies' gravitational forces interacted, pulling and twisting their shapes into bizarre, irregular forms. Gas clouds within the galaxies collided, triggering bursts of new star formation and igniting the birth of future stellar generations. But the real game changers in these collisions were the supermassive black holes at the centers of the galaxies. When two galaxies merged, their black holes eventually spiraled toward each other, drawn by gravity. As they inched closer, they began to orbit one another, creating ripples in space-time known as gravitational waves. Eventually, these black holes would collide, releasing an enormous amount of energy and sending shock waves through the surrounding gas and dust. These mergers not only created even more massive black holes, but also influenced the growth of galaxies around them. The aftermath of these collisions was equally fascinating. The energy released during the mergers heated the surrounding gas, preventing it from cooling and forming new stars. This process, known as feedback, helped regulate the growth of galaxies, ensuring they didn't grow too large too quickly. At the same time, the collisions redistributed gas and dust, creating the conditions for future star formation in other regions of the merged galaxy. Scientists study these ancient collisions by observing distant galaxies and using computer simulations to recreate the conditions of the early universe. By analyzing the light from these galaxies, researchers can identify telltale signs of past mergers, such as distorted shapes, unusual star formation patterns, and the presence of multiple black holes. These clues help us piece together how these cosmic collisions influenced the evolution of the universe. The first cosmic collisions were more than just violent encounters. They were essential building blocks of the universe's structure. They drove the growth of galaxies, shaped the distribution of matter, and even influenced the formation of the cosmic web. As we continue to explore the mysteries of the cosmic dawn era, these collisions remind us of the dynamic and ever-changing nature of the cosmos. Next, we'll explore another intriguing force that shaped the early universe, cosmic feedback. How did the first stars and black holes regulate the growth of galaxies, and what role did they play in the universe's evolution? Stay tuned as we uncover more secrets of this extraordinary era. Now, let's shift our focus to a fascinating process that shaped the early universe, cosmic feedback. This phenomenon, driven by the first stars and black holes, played a crucial role in regulating how galaxies grew and evolved. Without it, the universe might look very different today. Cosmic feedback is essentially the way energy and matter are recycled in the cosmos. When the first stars formed, they didn't just sit quietly in the darkness. They were incredibly active, emitting intense radiation and powerful stellar winds. As these stars reached the end of their lives, many exploded as supernova, releasing vast amounts of energy and heavy elements into their surroundings. This energy heated up the surrounding gas, making it too hot to collapse and form new stars. In this way, the first stars acted like cosmic regulators, controlling the pace of star formation in their galaxies. But stars weren't the only players in this feedback process. The supermassive black holes at the centers of early galaxies also had a major role to play. As these black holes consumed gas and dust, they released enormous amounts of energy in the form of radiation and jets of particles. These jets could travel vast distances, heating up gas far beyond the black hole's immediate vicinity. This process, known as active galactic nucleus feedback, prevented gas from cooling and forming stars, effectively putting a brake on galaxy growth. Interestingly, cosmic feedback wasn't just about stopping star formation, it also helped shape the distribution of matter in the universe. By heating and redistributing gas, feedback created pockets of dense material that could later collapse to form new stars and galaxies. It also played a key role in building the cosmic web, the large-scale structure of the universe that connects galaxies across vast distances. Scientists study cosmic feedback by observing distant galaxies and using sophisticated computer simulations. These tools allow researchers to trace how energy from stars and black holes influenced the growth of galaxies over billions of years. By analyzing the light from these ancient galaxies, astronomers can identify signs of feedback, such as unusually high temperatures or the presence of heavy elements in intergalactic gas. Cosmic feedback reminds us that the universe is a dynamic, interconnected system. The first stars and black holes didn't just exist in isolation, they actively shaped their surroundings, influencing the evolution of galaxies and the structure of the cosmos itself. As we continue to explore the mysteries of the cosmic dawn era, feedback stands out as a key process that helped create the universe we see today. Next, we'll dive into another intriguing mystery, the first cosmic metals. How did the earliest heavy elements form, and how did they spread throughout the universe? Stay tuned as we uncover more secrets of this extraordinary era. Now, let's turn our attention to one of the most transformative mysteries of the cosmic dawn era, the first cosmic metals. These elements, heavier than helium, were the building blocks for everything from planets to life itself. But how did they come to exist in a universe that started with only hydrogen and helium? The answer lies in the fiery hearts of the first stars and the explosive events that marked their deaths. When the universe was young, it was a simple place composed almost entirely of hydrogen and helium. There were no metals, no carbon, no oxygen, no iron, just the lightest elements forged in the aftermath of the Big Bang. But as the first stars, known as Population 3 stars, ignited, they began to change the cosmic landscape. These stars were massive, far larger than the Sun, and burned through their fuel at an incredible rate. Deep within their cores, nuclear fusion transformed hydrogen and helium into heavier elements like carbon, oxygen, and even iron. This process, known as nucleosynthesis, was the first step in creating the metals that would later shape the universe. However, the story doesn't end there. When these massive stars reached the end of their lives, they didn't fade quietly. They exploded in spectacular supernovae. These explosions were so powerful that they scattered the newly formed metals across vast regions of space. The shock waves from these supernovae also triggered the collapse of nearby gas clouds, seeding the formation of new stars and galaxies. In this way, the first metals didn't just enrich the universe, they helped drive its evolution. But the distribution of these metals wasn't uniform. Some regions of the early universe became rich in heavy elements, while others remained relatively pristine. This uneven distribution had profound implications for the formation of galaxies and the emergence of planetary systems. For example, regions with higher concentrations of metals were more likely to form stars with rocky planets, while metal-poor regions might have given rise to stars with fewer planets or none at all. Scientists study the first cosmic metals by analyzing the light from ancient stars and galaxies. By examining the spectra of this light, astronomers can identify the chemical fingerprints of elements like carbon, oxygen, and iron. These observations reveal not only the presence of metals but also how they were distributed across the early universe. Additionally, computer simulations help researchers model the processes that spread these elements, offering insights into how the first metals shaped the cosmos. The mystery of the first cosmic metals is a reminder of how interconnected the universe truly is. The elements that make up our world and even our bodies were forged in the hearts of stars that lived and died billions of years ago. As we continue to explore the cosmic dawn era, the story of these metals offers a glimpse into the origins of the complex, diverse universe we inhabit today. Next, we'll explore another fascinating process, the first cosmic ionization fronts. How did these boundaries between ionized and neutral gas shape the early universe? Stay with us as we uncover more secrets of this extraordinary era. Now, let's shift our focus to another pivotal phenomenon of the cosmic dawn era, the first cosmic ionization fronts. These invisible boundaries where ionized gas met neutral gas played a crucial role in shaping the early universe. But what exactly are ionization fronts, and how did they influence the cosmos during this transformative period? To understand ionization fronts, we need to revisit the state of the universe shortly after the Big Bang. Initially, the universe was filled with neutral hydrogen gas, a sea of atoms that absorbed light and kept the cosmos in darkness. But as the first stars and galaxies began to form, their intense radiation started to ionize this gas, stripping electrons from hydrogen atoms and turning them into charged particles. This process created regions of ionized gas that expanded outward, pushing against the surrounding neutral gas. The boundary between these two states, ionized and neutral, is what we call an ionization front. These fronts didn't just sit still, they moved. As more stars and galaxies formed, their radiation continued to ionize the gas around them, causing the fronts to propagate through space. Think of it like a wave moving through water, except this wave was made of light and energy, carving out bubbles of ionized gas in the cosmic sea. These bubbles grew larger over time, eventually overlapping and merging, which helped to reionize the entire universe. But the story of ionization fronts isn't just about their movement, it's also about their impact. As these fronts advanced, they heated the surrounding gas, altering its properties and influencing the formation of future stars and galaxies. For instance, the increased temperature made it harder for gas to collapse and form new stars, slowing down star formation in some regions. At the same time, the ionized gas became more transparent, allowing light to travel farther and illuminating the universe in ways that hadn't been possible before. Scientists study these ionization fronts by observing the light from distant quasars and galaxies. By analyzing the absorption lines in their spectra, astronomers can map the distribution of ionized and neutral gas, revealing how these fronts propagated and interacted with their surroundings. Computer simulations also play a key role, helping researchers model the complex physics of ionization and predict how these fronts shaped the early universe. The mystery of the first cosmic ionization fronts reminds us of the delicate balance between light and matter in the cosmos. These fronts were not just passive boundaries, they were active agents of change, driving the transition from a dark, neutral universe to one filled with light and structure. As we continue to explore the cosmic dawn era, the story of ionization fronts offers a fascinating glimpse into the forces that shape the universe we see today. Next, we'll delve into another intriguing mystery, the first cosmic shadows. How did these dark regions influence the distribution of light in the early universe? Stay with us as we uncover more secrets of this extraordinary era. Now, let's turn our attention to another captivating mystery of the cosmic dawn era, the first cosmic shadows. These shadows, cast by dense regions of gas, played a surprising role in shaping the way light traveled through the early universe. But what exactly were these shadows, and how did they leave their mark on the cosmos? To understand cosmic shadows, we need to picture the universe during this era as a patchwork of light and darkness. As the first stars and galaxies began to shine, their light didn't travel freely through space. Instead, it encountered dense clouds of gas regions where matter was packed tightly together. These clouds acted like cosmic curtains, absorbing and blocking light, creating shadows that stretched across the universe. These weren't shadows in the traditional sense, like those cast by a tree on a sunny day. Instead, they were vast, diffuse regions where light struggled to pass through, leaving behind patterns of brightness and darkness. These shadows had a profound impact on the distribution of light in the early universe. As light from the first stars and galaxies passed through these dense gas clouds, it was absorbed and scattered, altering its path and intensity. This process created a kind of cosmic filter, shaping how light spread through space and influencing what we see today when we look back at this era. In some regions, the shadows allowed light to pass through more easily, creating bright patches. In others, they blocked light entirely, leaving behind dark voids. This interplay of light and shadow helped to define the structure of the early universe, setting the stage for the formation of galaxies and larger cosmic structures. But the mystery deepens when we consider how these shadows formed in the first place. Scientists believe that the dense gas clouds responsible for casting these shadows were remnants of the primordial universe regions where matter had clumped together more tightly than elsewhere. These clumps may have been influenced by the faint ripples of density left over from the Big Bang, which acted as seeds for the formation of structures. Over time, these regions grew denser, eventually becoming thick enough to block light and cast shadows across the cosmos. Studying these shadows isn't easy, but astronomers have developed clever ways to detect their presence. By analyzing the light from distant quasars and galaxies, they can identify the telltale signs of absorption caused by these dense gas clouds. These observations reveal not only where the shadows existed, but also how they evolved over time. Computer simulations also play a crucial role, helping researchers model the behavior of these gas clouds and predict how they influenced the distribution of light in the early universe. The mystery of the first cosmic shadows reminds us that even in the vastness of space, light and darkness are deeply intertwined. These shadows weren't just passive features. They were active participants in the story of the universe's evolution, shaping the way light traveled and influencing the formation of the structures we see today. As we continue to explore the cosmic dawn era, the study of these shadows offers a unique window into the delicate balance between light and matter in the early cosmos. Next, we'll explore another fascinating phenomenon, the first cosmic echoes. How did these echoes, remnants of the Big Bang, influence the cosmic dawn era? Stay with us as we uncover more secrets of this extraordinary time. Now, let's shift our focus to another intriguing mystery of the cosmic dawn era, the first cosmic echoes. These echoes, remnants of the Big Bang, hold clues to how the early universe evolved and shaped the conditions for the first stars and galaxies to form. But what exactly are these echoes, and how did they leave their mark on the cosmic dawn? To understand cosmic echoes, we need to go back to the very beginning, the Big Bang itself. This colossal event didn't just create the universe, it also sent ripples through the fabric of space and time. These ripples, known as gravitational waves, traveled outward, carrying with them information about the universe's earliest moments. Think of them like the vibrations from a bell that continue to resonate long after it's been struck. In the case of the Big Bang, these vibrations were the first cosmic echoes, spreading through the cosmos and influencing everything in their path. During the cosmic dawn era, these echoes played a subtle but significant role. As the universe expanded and cooled, the gravitational waves from the Big Bang interacted with the matter and energy around them. They didn't just pass through space unnoticed, they subtly altered the density and distribution of matter, creating tiny fluctuations that would later grow into the seeds of galaxies and larger cosmic structures. These echoes acted like a cosmic blueprint, guiding the formation of the universe's first structures in ways we're only beginning to understand. One of the most fascinating aspects of these echoes is how they connect the Big Bang to the cosmic dawn. The gravitational waves from the Big Bang carried with them information about the universe's initial conditions, its temperature, density, and even the rate of its expansion. As these waves traveled through the early universe, they left behind a kind of fingerprint, imprinting their influence on the gas and dust that would eventually form stars and galaxies. This means that the echoes of the Big Bang didn't just shape the cosmic dawn. They also preserved a record of the universe's earliest moments, waiting to be decoded by astronomers. Detecting these echoes isn't easy, but scientists have made remarkable progress in recent years. Advanced instruments like gravitational wave detectors have allowed researchers to observe these ripples in space-time, providing a glimpse into the universe's infancy. By studying these signals, astronomers can piece together how the first cosmic echoes influenced the formation of the first stars and galaxies. Computer simulations also play a key role, helping researchers model how these echoes interacted with matter and shaped the early universe. The mystery of the first cosmic echoes reminds us that the universe is full of hidden connections. These echoes, born from the Big Bang, traveled across billions of years to influence the cosmic dawn, shaping the universe we see today. As we continue to explore this era, the study of these echoes offers a unique window into the universe's origins, revealing how even the faintest vibrations from the past can leave a lasting impact on the cosmos. Next, we'll delve into another captivating mystery, the first cosmic seeds. How did these tiny fluctuations in density grow into the galaxies and clusters we see today? Stay with us as we uncover more secrets of the cosmic dawn era. Now, let's turn our attention to the mystery of the first cosmic seeds. These tiny fluctuations in density, almost imperceptible ripples in the fabric of the early universe, hold the key to understanding how the vast cosmic structures we see today came to be. But how did these minuscule variations grow into the galaxies, clusters, and even the cosmic web that defines our universe? To grasp the significance of these cosmic seeds, we need to rewind to the moments just after the Big Bang. At that time, the universe was a hot, dense soup of particles and energy, but it wasn't perfectly uniform. Tiny differences in density, some regions slightly denser, others slightly less dense, existed throughout. These fluctuations, though incredibly small, were the first cosmic seeds. They were like the faintest whispers in a silent room, barely noticeable but destined to grow louder over time. As the universe expanded and cooled, gravity began to play its part. The slightly denser regions had a stronger gravitational pull, attracting more matter toward them. Over billions of years, these regions grew denser and denser, eventually collapsing under their own gravity to form the first stars, galaxies, and clusters. The less dense regions, on the other hand, became the vast, empty voids we see between galaxies today. In this way, the cosmic seeds acted as the foundation for the universe's large-scale structure, shaping everything from the smallest galaxies to the largest superclusters. One of the most remarkable aspects of these seeds is how they connect the Big Bang to the universe we observe today. The patterns of these early fluctuations are imprinted in the cosmic microwave background, the afterglow of the Big Bang. By studying this ancient light, astronomers can map the distribution of these seeds and trace their evolution over cosmic time. It's like uncovering a fossil record of the universe's infancy, revealing how the tiniest variations grew into the cosmic giants we see now. But the mystery doesn't end there. Scientists are still trying to understand what caused these fluctuations in the first place. One leading theory points to quantum mechanics, suggesting that these tiny density variations originated from quantum fluctuations in the very early universe. These fluctuations, amplified by the rapid expansion of space during cosmic inflation, became the seeds of structure. If this theory holds, it means that the galaxies and clusters we see today owe their existence to the quantum world, a fascinating link between the smallest scales of physics and the largest structures in the cosmos. The study of these cosmic seeds is not just about understanding the past, it also sheds light on the future. By modeling how these seeds grew into galaxies and clusters, scientists can predict how the universe will continue to evolve. Will the cosmic web become even more intricate? Will galaxies continue to merge and grow? These are questions that the mystery of the first cosmic seeds helps us explore, offering a glimpse into the universe's ongoing story. As we unravel the secrets of these seeds, we're reminded of the profound interconnectedness of the cosmos. From the tiniest quantum fluctuations to the grandest galaxies, the universe is a tapestry woven together by the threads of its earliest moments. And as we continue to explore, the mystery of the first cosmic seeds invites us to ponder how even the smallest beginnings can shape the vastness of the cosmos. Next, we'll explore another captivating enigma, the first cosmic clocks. How did these early timekeepers form, and what do they reveal about the universe's history? Stay with us as we uncover more mysteries of the cosmic dawn era. Now, let's shift our focus to another fascinating mystery, the first cosmic clocks. These natural timekeepers, like pulsars, offer us a unique window into the early universe, helping us measure time on a cosmic scale and uncover secrets about the universe's history. But what exactly are these cosmic clocks, and how did they come to be? Pulsars, often referred to as the universe's lighthouses, are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. These beams sweep across space like the light from a lighthouse, and when they point toward Earth, we detect them as regular pulses of radiation. This precise regularity makes pulsars some of the most accurate clocks in the cosmos. But how did these cosmic timekeepers form in the first place? The story of pulsars begins with the death of massive stars. When a star several times more massive than our Sun exhausts its nuclear fuel, it undergoes a catastrophic explosion known as a supernova. The outer layers of the star are blasted into space while the core collapses under its own gravity. If the core is dense enough, it forms a neutron star, a city-sized object with the mass of a star packed into a sphere just a few kilometers across. Some of these neutron stars are born spinning rapidly, and their intense magnetic fields channel radiation into narrow beams, creating the pulsating signals we observe. But pulsars aren't just fascinating objects, they're also invaluable tools for astronomers. Their incredibly stable pulses allow scientists to measure time with extraordinary precision. In fact, some pulsars are so regular that they rival atomic clocks here on Earth. This precision makes them ideal for studying phenomena like gravitational waves, the warping of spacetime predicted by Einstein's theory of relativity. By monitoring the pulses from multiple pulsars, astronomers can detect subtle changes in their timing caused by passing gravitational waves, providing a new way to observe these ripples in the fabric of the universe. Beyond their role as cosmic clocks, pulsars also offer clues about the conditions of the early universe. The oldest pulsars we've discovered are remnants of some of the first generations of stars, giving us a glimpse into the era when the universe was young and filled with the raw materials for star formation. By studying these ancient pulsars, scientists can piece together how the first stars lived and died, enriching the cosmos with heavy elements and paving the way for future generations of stars and planets. One of the most intriguing aspects of pulsars is their potential to reveal the universe's expansion history. As pulsars age, their rotation slows down and their pulses become less frequent. By measuring this slowdown, astronomers can estimate the age of pulsars and use them to trace the timeline of cosmic events. This information helps us understand how the universe has evolved over billions of years, from the formation of the first stars to the present day. The mystery of the first cosmic clocks reminds us that even the most distant and exotic objects in the universe can serve as tools for understanding our cosmic origins. Pulsars, with their precise pulses and ancient origins, are more than just celestial curiosities. They're keys to unlocking the secrets of the early universe. As we continue to study these remarkable objects, we gain new insights into the forces that shape the cosmos and the intricate dance of time and space that defines our universe. Next, we'll delve into another captivating enigma, the first cosmic shadows. How did these early phenomena influence the distribution of light in the universe, and what do they tell us about the cosmic dawn era? Stay tuned as we uncover more mysteries of the cosmos. Now, let's turn our attention to a phenomenon that shaped the early universe in ways we're only beginning to understand: the first cosmic shadows. These shadows, cast by dense regions of gas, played a crucial role in how light traveled through the cosmos during the cosmic dawn era. But what exactly were these shadows, and how did they influence the universe's evolution? In the early universe, light didn't travel freely as it does today. Instead, it had to navigate through a thick fog of neutral hydrogen gas, which absorbed and scattered the light from the first stars and galaxies. Dense pockets of this gas acted like cosmic barriers, casting shadows that blocked or altered the path of light. These shadows weren't just empty spaces. They were regions where the gas was so thick that it absorbed the light passing through, creating dark patches in an otherwise glowing universe. These first cosmic shadows were more than just obstacles. They were markers of the universe's structure. The dense regions of gas that created them were the seeds of future galaxies and galaxy clusters. As gravity pulled these gas clouds together, they began to collapse, forming the first stars and galaxies. The shadows they cast were like fingerprints, revealing the distribution of matter in the early universe and giving astronomers clues about how large-scale structures began to form. One of the most fascinating aspects of these shadows is how they influenced the reionization of the universe. As the first stars and galaxies formed, their intense ultraviolet light began to ionize the surrounding gas, breaking apart the neutral hydrogen atoms and clearing the cosmic fog. But this process wasn't uniform. The dense regions of gas that cast shadows resisted ionization longer, creating a patchwork of ionized and neutral regions. This uneven reionization left its mark on the cosmic microwave background, the afterglow of the Big Bang, and provides a record of how light and matter interacted in the early universe. Studying these shadows is no easy task because they existed so long ago. Their light has been stretched and dimmed by the expansion of the universe, making them incredibly faint and difficult to detect. However, advances in telescopes and observational techniques are allowing astronomers to peer deeper into the cosmos than ever before. By analyzing the subtle variations in the cosmic microwave background and the light from distant quasars, scientists can map the distribution of these ancient shadows and piece together the story of how the universe transitioned from darkness to light. The mystery of the first cosmic shadows reminds us that even the darkest corners of the universe hold clues to its origins. These shadows, cast by the earliest structures, shaped the way light traveled through the cosmos and influenced the formation of the galaxies we see today. As we continue to explore these ancient phenomena, we gain a deeper understanding of the forces that shaped the universe and the intricate interplay between light and matter. Next, we'll explore another intriguing puzzle, the first cosmic echoes. How did these remnants of the Big Bang influence the cosmic dawn era, and what do they tell us about the universe's earliest moments? Stay with us as we uncover more secrets of the cosmos. Now, let's shift our focus to another fascinating mystery, the first cosmic echoes. These echoes, remnants of the Big Bang, offer a unique window into the universe's earliest moments and how they shaped the cosmic dawn era. But what exactly are these echoes, and what do they reveal about the birth of the cosmos? When the Big Bang occurred, it didn't just create the universe, it sent ripples through the fabric of space and time. These ripples, known as gravitational waves, are like cosmic echoes that have been traveling through the universe ever since. During the cosmic dawn era, these waves may have played a crucial role in influencing the formation of the first stars and galaxies. Imagine these gravitational waves as subtle vibrations, gently nudging the dense clouds of gas and dark matter, helping them collapse and ignite the first stars. But gravitational waves aren't the only echoes from the Big Bang. The cosmic microwave background, often called the afterglow of the Big Bang, also carries faint imprints of these early vibrations. These imprints are like a cosmic fingerprint, revealing the density and temperature fluctuations in the universe just moments after its birth. By studying these patterns, scientists can piece together how these early fluctuations grew into the vast cosmic structures we see today. One of the most intriguing questions is how these echoes influenced the distribution of matter during the cosmic dawn era. Did they help create the first seeds of galaxies, or did they simply pass through, leaving no lasting impact? Some theories suggest that these echoes may have amplified certain regions of density, making it easier for stars and galaxies to form. Others propose that they played a more subtle role, shaping the large-scale structure of the universe in ways we're only beginning to understand. Detecting these ancient echoes is no small feat. Gravitational waves from the Big Bang are incredibly faint, and their signals have been stretched and weakened over billions of years. However, advancements in technology, such as space-based observatories and highly sensitive detectors, are bringing us closer to uncovering these elusive signals. By capturing these echoes, we can gain new insights into the conditions of the early universe and how they set the stage for the cosmic dawn. The mystery of the first cosmic echoes reminds us that the universe is full of hidden stories waiting to be uncovered. These echoes, born from the Big Bang, carry the secrets of how the cosmos began and how it evolved into the vibrant universe we see today. As we continue to explore these ancient signals, we move closer to understanding the forces that shaped the universe's earliest moments. Next, we'll delve into another captivating puzzle, the first cosmic seeds. How did tiny fluctuations in density grow into the galaxies and clusters we see today? Stay with us as we uncover more secrets of the cosmic dawn era. Now, let's turn our attention to one of the most fundamental mysteries of the cosmic dawn era, the first cosmic seeds. These seeds, tiny fluctuations in density, were the building blocks of everything we see in the universe today. But how did these minuscule ripples in the early universe grow into the vast galaxies and clusters that fill the cosmos? To understand this, we need to go back to the very beginning. In the moments after the Big Bang, the universe was a hot, dense soup of particles and energy. But it wasn't perfectly smooth. Tiny variations in density existed, like ripples on the surface of a pond. These fluctuations, though incredibly small, were the first cosmic seeds. Over time, gravity began to pull on these denser regions, causing them to grow and collapse, eventually forming the first stars, galaxies, and larger structures. One of the most fascinating aspects of these seeds is how they were created. Scientists believe they originated from quantum fluctuations during the universe's rapid expansion, known as cosmic inflation. These fluctuations were stretched across the cosmos, leaving behind a faint imprint that would later become the blueprint for all cosmic structures. It's like planting a garden. The seeds were sown in the early universe, and gravity acted as the gardener, nurturing them into the galaxies we see today. But how did these tiny seeds grow so dramatically? The answer lies in the interplay between dark matter and ordinary matter. Dark matter, which makes up most of the universe's mass, formed invisible halos around these dense regions. These halos acted as gravitational wells, pulling in gas and dust, which eventually collapsed to form stars and galaxies. Without dark matter, the universe might have remained a featureless expanse with no galaxies, no stars, and no planets. The cosmic microwave background, the afterglow of the Big Bang, provides crucial evidence for these early seeds. The faint temperature variations in this ancient light reveal the density fluctuations that existed just 380,000 years after the Big Bang. By studying these patterns, scientists can trace how these seeds evolved over billions of years, growing into the cosmic web of galaxies and clusters we observe today. One of the biggest questions is why these seeds grew at different rates. Some regions of the universe became densely packed with galaxies, while others remained relatively empty. This uneven growth is thought to be influenced by the initial size and distribution of the seeds, as well as the complex interactions between dark matter, gas, and radiation during the cosmic dawn era. Understanding this process is key to unraveling the mystery of how the universe evolved from a nearly uniform state to the intricate structure we see today. The mystery of the first cosmic seeds reminds us that even the smallest beginnings can lead to the grandest outcomes. These tiny fluctuations, born in the earliest moments of the universe, set the stage for the formation of everything: stars, galaxies, and even us. As we continue to study these ancient seeds, we gain a deeper understanding of how the universe grew from a chaotic beginning into the ordered cosmos we call home. Next, we'll explore another intriguing puzzle: the first cosmic clocks. How did these early timekeepers form, and what do they tell us about the universe's history? Stay with us as we uncover more secrets of the cosmic dawn era. Now, let's shift our focus to another fascinating mystery of the cosmic dawn era: the first cosmic clocks. These natural timekeepers, like pulsars, offer us a unique window into the early universe, helping us measure time on a cosmic scale and uncover secrets about its history. But how did these cosmic clocks form, and what can they tell us about the universe's infancy? Pulsars, often referred to as the universe's lighthouses, are rapidly spinning neutron stars that emit beams of radiation. These beams sweep across space like the light from a lighthouse, and their incredibly regular pulses make them some of the most precise clocks in the cosmos. But pulsars didn't just appear out of nowhere. They are the remnants of massive stars that ended their lives in spectacular supernova explosions. When these stars collapsed, their cores were crushed into incredibly dense neutron stars, some of which became pulsars. The formation of pulsars is tied to the life cycles of the first massive stars in the universe. These stars, born from the collapse of dense gas clouds during the cosmic dawn era, lived fast and died young. When they exploded as supernova, they left behind neutron stars, some of which began spinning rapidly and emitting those characteristic pulses of radiation. These pulsars became the first cosmic clocks, ticking away with remarkable precision. But why are pulsars so important for understanding the early universe? Their regular pulses act like cosmic metronomes, allowing scientists to measure time and distance in space with incredible accuracy. By studying the timing of these pulses, astronomers can detect subtle changes in the fabric of space-time, such as the presence of gravitational waves. These ripples in space-time, predicted by Einstein's theory of general relativity, carry information about cataclysmic events like the mergers of black holes or neutron stars. Pulsars, in a sense, are the universe's way of keeping time and recording its history. Another intriguing aspect of pulsars is their role in mapping the universe. Because their pulses are so regular, any delay or distortion in their signals can reveal the presence of interstellar gas, magnetic fields, or even dark matter. This makes pulsars not just clocks but also cosmic probes, helping us understand the environment of the early universe and how it evolved over billions of years. One of the most exciting discoveries involving pulsars is their potential to reveal the nature of dark matter. Some theories suggest that dark matter particles could interact with pulsars, subtly altering their pulses. By carefully monitoring these changes, scientists hope to uncover clues about the elusive substance that makes up most of the universe's mass. Pulsars, in this way, are more than just timekeepers. They are tools for exploring the deepest mysteries of the cosmos. The first cosmic clocks remind us that even in the vastness of space, time is a fundamental thread that connects everything. From the explosive deaths of massive stars to the precise ticks of pulsars, these natural timekeepers help us piece together the story of the universe's origins. As we continue to study them, we gain not just a better understanding of time, but also a deeper appreciation for the intricate processes that shape the cosmos. With that, we've reached the end of our journey through the 50 mysteries of the cosmic dawn era. From the first stars to the cosmic clocks, each mystery has revealed a piece of the puzzle, showing us how the universe grew from a chaotic beginning into the ordered cosmos we see today. Thank you for joining us on this exploration of the universe's earliest moments. If you enjoyed this deep dive into the mysteries of space, don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep looking up as we wrap up our journey through the 50 mysteries of the cosmic dawn era. It's clear that this period in the universe's history is filled with questions that push the boundaries of our understanding. From the formation of the first stars to the enigmatic behavior of dark matter, each mystery challenges us to rethink what we know about the origins of the cosmos. These puzzles remind us that the universe is far more complex and wondrous than we can imagine, and that every discovery leads to even more questions waiting to be answered. The cosmic dawn era was a time of transformation when the universe transitioned from darkness to light, from simplicity to complexity. It's a story of how the first structures emerged, how the first elements were forged, and how the seeds of everything we see today were planted. Yet, despite the incredible progress we've made, many of these mysteries remain unsolved. What triggered the end of the cosmic dark ages? How did the first supermassive black holes form so quickly? And what role did dark energy play in shaping the early universe? These are just a few of the questions that continue to captivate scientists and stargazers alike. As we reflect on these mysteries, it's worth considering how much we still have to learn. The universe is a vast, ever-changing tapestry, and each thread we unravel reveals new patterns and connections. The cosmic dawn era is a reminder that science is a journey, not a destination, and that every discovery brings us closer to understanding our place in the cosmos. Now it's your turn to join the conversation. What do you think about these cosmic mysteries? Which one fascinates you the most? Share your thoughts in the comments below. We'd love to hear your ideas and theories. And if you enjoyed this deep dive into the mysteries of the universe, don't forget to like, subscribe, and hit the notification bell for more cosmic explorations. There's so much more to uncover, and we can't wait to take you on the next adventure. Until then, keep looking up and wondering about the incredible universe